Close your eyes. No, really. Close them. What do you see? Darkness, probably. Maybe some phosphine patterns drifting behind your eyelids. But even that darkness is something. It is the absence of light registered by a functioning brain inside a skull, inside a universe that exists. Now try to imagine a darkness with no one to see it. No space for it to occupy. No time for it to pass through. That is where we begin. This is a documentary about everything. Not everything in some loose, hand-wavy, motivational poster sense. Everything. The totality of matter, energy, space, and time. Every photon that has ever traveled. Every atom that has ever bonded. Every star that has ever burned, and every civilization that has ever crumbled. All of it. And we're going to start before any of it existed, because that is where the story actually begins. The question that has haunted every physicist, philosopher, and insomniac who has ever stared at a ceiling at 3 in the morning is deceptively simple. Why is there something rather than nothing? It sounds like a question for a philosophy seminar. But modern physics has taken it deadly seriously. And the answers, if you can call them that, are far stranger and far more disturbing than anything philosophy ever proposed. Let us start with nothing. True nothing. Not empty space, because space itself is something. Not a vacuum, because even a vacuum has quantum fields humming through it. We're talking about the absence of dimensions, the absence of time, the absence of physical law. A state so thoroughly empty that even the concept of emptiness does not apply. Physicists call it the pre-geometric state. Philosophers call it deeply unsettling. They're both right. Here is the first uncomfortable truth of this documentary. Nothingness, as far as modern physics can tell, is not stable. It never was. The mathematics of quantum mechanics suggest that a state of absolute nothing is inherently unstable. It fluctuates. It shimmers. Given enough non-time and enough non-space, nothingness will inevitably produce something. Not because something wanted to exist, but because nothing could not hold itself together. The physicist Lawrence Krauss called this a universe from nothing. The idea is elegant in its bleakness. Quantum fluctuations in the void can spontaneously generate bubbles of space-time, tiny, ephemeral pockets of something that pop into existence and vanish almost instantly. Almost, because very rarely one of those bubbles does not vanish. It inflates. It expands. It becomes a universe. Our universe, perhaps, was one such accident. But Krauss's proposal, elegant as it is, merely pushes the question back one step. Where did the quantum fields come from? Where did the laws that govern those fluctuations originate? You pull one thread and the whole tapestry of causation unravels into an infinite regress. Turtles all the way down, as the old joke goes. Except these turtles are made of mathematics, and they may not be standing on anything at all. Enter eternal inflation. This is the idea proposed by physicist Andrei Linde in the early 1980s that inflation, the rapid exponential expansion of space, did not just happen once. It is happening always, everywhere, in a vast, perhaps infinite metaspace that Linde called the inflationary multiverse. Our observable universe is one bubble in an endlessly fizzing ocean of bubble universes, each with potentially different physical constants, different laws, different fates. Let that settle for a moment. If eternal inflation is correct, our cosmos is not the cosmos. It is a cosmos, one of perhaps infinitely many. Some of those other universes might have 3 dimensions of space, like ours. Others might have 7, or 11, or none. Some might have nuclear forces too weak to hold atoms together. Others might collapse back into nothing within microseconds of their birth. We happen to get the set of laws that permits stars, chemistry, and, eventually, someone to make a documentary about it. This is what physicists call the anthropic principle, and it makes some of them deeply uncomfortable. It is not an explanation so much as an observation disguised as one. Why are the laws of physics fine-tuned to permit complex structures? Because if they were not, we would not be here to ask the question. It is logically airtight and scientifically unsatisfying in equal measure. It is the cosmic equivalent of answering, "Why did I win the lottery?" with "Because someone had to." Not everyone is comfortable with a multiverse. The physicist Paul Steinhardt, one of inflation's original architects, has become one of its fiercest critics. He argues that a theory predicting everything predicts nothing. If every possible universe exists somewhere, then eternal inflation cannot be tested, cannot be falsified, and therefore, by the standards of Karl Popper and the scientific method, is not really science at all. It is theology with better mathematics. There are alternatives, of course. The cyclic model, championed by Steinhardt and Neil Turok, proposes that the Big Bang was not the beginning, but merely the latest bounce in an infinite series of expansions and contractions. The universe breathes. It expands, cools, empties, contracts, and detonates again, over and over across timescales that make even cosmologists reach for a stiff drink. No beginning, no end, just an eternal heartbeat of creation and destruction. Then there's the proposal from Stephen Hawking and James Hartle, the no-boundary condition. In this model, time does not have a beginning in the way we usually imagine. Instead, as you trace the universe backwards, time itself gradually transforms into a spatial dimension, like the way lines of longitude converge at the North Pole. There is no edge, no first moment, no point where you can plant a flag and say, "Here, this is where it all started." Hawking described it beautifully. Asking what came before the Big Bang, he said, is like asking what is south of the South Pole. The question sounds sensible, but it is built on a misunderstanding of the geometry involved. Time, in the Hartle-Hawking model, is finite but unbounded. It has a shape, but no beginning. The universe simply is, always was, and always will be, not in the sense of being eternal, but in the deeper sense of existing outside the framework of before and after. If you find all of this confusing, congratulations. You are paying attention. The honest answer to what came before the Big Bang is that we do not know. We have hypotheses, some of them beautiful, some of them terrifying, none of them proven. The pre-Big Bang era is where physics meets philosophy at a dark crossroads, and neither one is entirely sure which way to turn. But here's what we do know. We know that 13.8 billion years ago, give or take about 20 million years, the observable universe was in an extraordinarily hot, extraordinarily dense state. We know this because we can see the afterglow. We can measure it. We can photograph it. The cosmic microwave background radiation is, quite literally, a baby photo of the universe, taken when it was only 380,000 years old. And it matches our models with eerie, almost uncomfortable precision. The Planck satellite, launched by the European Space Agency in 2009, mapped this ancient light with a resolution that would have been unthinkable a generation earlier. What it found was a universe that was almost, but not quite, perfectly uniform. Tiny temperature fluctuations, variations of 1 part in 100,000, rippled across the infant cosmos. Those fluctuations are the seeds of everything. Every galaxy, every star, every planet, every atom of your body traces its lineage back to those minuscule wrinkles in the primordial fire. Think about that for a moment. The Planck data is not just a map of the early universe. It is a map of potential. Every hot spot, every cold spot, corresponds to a region of slightly higher or lower density that will, over billions of years, grow into a cluster of galaxies or an immense cosmic void. You are looking at the architectural blueprint of all large-scale structure in the observable universe, written in microwave light 13.8 billion years ago. But blueprints need a builder, and in cosmology, that builder is gravity. The densest regions in the early universe had slightly stronger gravitational pull. They attracted more matter. That matter made them denser still, which attracted more matter, in a snowball effect that physicists call gravitational instability. Give it enough time, and those tiny initial overdensities will collapse into the cosmic web of filaments, clusters, and voids that we observe today. And then there is the question of dark matter. the substance that makes up roughly 27% of the total energy budget of the universe, yet has never been directly detected. We know it is there because galaxies rotate too fast, galaxy clusters are too massive, and gravitational lensing bends light in ways that visible matter alone cannot explain. Dark matter is the invisible scaffolding of the cosmos, and without it, nothing we see would hold together. What is dark matter? We do not know. That sentence, "we do not know," is going to recur in this documentary with alarming frequency. And if that bothers you, good. Science is not a cathedral of certainties. It is a construction site of provisional answers surrounded by scaffolding made of ignorance. Dark matter could be an undiscovered particle, a modification of gravity, or something so exotic that we have not yet developed the conceptual framework to imagine it. And then, as if the universe needed to be more mysterious, there is dark energy. Roughly 68% of the total energy density of the cosmos is composed of a substance, or a property of space itself, that drives the accelerating expansion of the universe. Discovered in 1998 through observations of distant type Ia supernovae, dark energy is perhaps the most profound and least understood phenomenon in all of physics. The universe is not just expanding, it is accelerating, and we have essentially no idea why. So here we stand, at the edge of knowledge, staring into a void that preceded everything. We are made of atoms forged in dying stars, organized by 4 billion years of evolution, running on a wet computer of neurons and synapses, trying to reconstruct the first fractions of a second of existence. The hubris is staggering. The results, honestly, are pretty impressive. Before we move on, let us sit with this uncertainty for one more moment. We do not know if the universe is the only one. We do not know if time has a beginning. We do not know what 95% of the cosmos is made of. And yet, we know its age to within 20 million years. We know its temperature to within microkelvins. We know its geometry is flat to within 1%. Ignorance and precision coexisting in the same sentence. That is modern cosmology. The void, it seems, was never truly empty. It was pregnant with possibility, trembling with quantum potential, and waiting, if waiting can even apply to a state without time, for the right fluctuation to set everything in motion. What came next was not a gentle unfolding. It was not a birth. It was a detonation. The most violent event in the history of everything, and it lasted less than a trillionth of a second. 13.8 billion years ago, the universe begins. Not with a sound, because there is no medium to carry sound. Not with a flash, because there are no eyes to see it and no photons free to travel. It begins with an event so far beyond the human capacity for metaphor that every analogy we reach for, an explosion, a birth, an awakening, collapses under the weight of its own inadequacy. The Big Bang is not like anything. It is the thing that everything else is like. Let us be precise about what happens, insofar as precision is possible when discussing events that last less than a billionth of a second. At time equals zero, or as close to zero as physics allows, the observable universe is compressed into a region smaller than a proton. Not the entire universe, mind you. The observable universe. The part we can see. The whole thing may be infinitely large, even at the beginning. That distinction matters, and it will keep physicists employed for centuries. The temperature at this moment exceeds 10 to the power of 32 Kelvin. That is a 1 followed by 32 zeros. For context, the surface of the Sun is a comparatively frosty 5,778 Kelvin. The core of the Sun, where nuclear fusion rages, is about 15 million Kelvin. We're talking about conditions that make the interior of a star look like a winter afternoon in Copenhagen. At these temperatures, matter, as we know it, cannot exist. Even the fundamental forces of nature are indistinguishable from one another. This is the Planck epoch, the first 10 to the minus 43 seconds of cosmic history. It is named after Max Planck, the German physicist who, in 1900, reluctantly introduced the idea of energy quanta and accidentally detonated a revolution in physics. During the Planck epoch, all four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are believed to be unified into a single superforce. What that superforce looks like, we have no idea. Our physics does not work here. The reason our physics fails is that the Planck epoch is where quantum mechanics and general relativity are both relevant simultaneously, and those two theories, the twin pillars of modern physics, are fundamentally incompatible. General relativity describes gravity as the curvature of smooth space-time. Quantum mechanics describes reality as probabilistic and granular. At the Planck scale, you need both, and they give contradictory answers. This is the holy grail of theoretical physics, the search for a theory of quantum gravity. String theory is one candidate. It proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings of energy, oscillating in 10 or 11 dimensions of space-time. Loop quantum gravity is another, suggesting that space-time itself is quantized, woven from discrete loops at the smallest scale. Both are mathematically sophisticated, both are unproven, and both have adherents who regard each other with a kind of collegial hostility usually reserved for rival football clubs. What we can say is that the Planck epoch ends when gravity separates from the other three forces at roughly 10 to the minus 43 seconds. This is the first symmetry-breaking event, and it is enormously consequential. Gravity, the weakest of the four forces but the one with infinite range, goes its own way, and the remaining three forces, still unified, carry on as the grand unified force. The universe has its first crack, its first differentiation, its first hint that uniformity will not last. At roughly 10 to the minus 36 seconds, the grand unified force itself fractures. The strong nuclear force, the force that will eventually bind quarks into protons and neutrons, separates from the electroweak force. This second symmetry-breaking event releases an enormous amount of energy, and it triggers something extraordinary: cosmic inflation. The universe, already expanding, begins to expand exponentially. Not fast, not very fast, incomprehensibly, absurdly, physics-breakingly fast. During inflation, which lasts from roughly 10 to the minus 36 to 10 to the minus 32 seconds, the universe expands by a factor of at least 10 to the 26 power. To put that in perspective, imagine a bacterium about 1 micrometer in size, suddenly expanding to the size of the observable universe. That is the scale of inflation. In a time interval shorter than the blink of an eye by a factor of a trillion, the cosmos goes from subatomic to cosmic. Alan Guth, who first proposed inflation in 1980, called it the ultimate free lunch. Why does inflation matter? Because it solves problems. The horizon problem. Why the universe looks the same in every direction, even in regions too far apart to have ever exchanged information. Inflation explains it. Those regions were once close together, in causal contact, before inflation flung them apart. The flatness problem. Why the geometry of the universe is so exquisitely flat. Inflation explains that too. Inflate a balloon enough, and any patch of its surface looks flat. The universe is that patch. But inflation does something else, something almost poetic. The quantum fluctuations that existed in the pre-inflationary universe, those tiny, random, probabilistic ripples in the quantum fields, get stretched by inflation to macroscopic scales. Quantum noise becomes cosmic structure. The randomness of the very small becomes the architecture of the very large. Every galaxy, every void, every cluster of galaxies you have ever seen in a Hubble image began as a quantum hiccup amplified by inflation into the scaffolding of reality. Inflation ends at around 10 to the minus 32 seconds. The inflatant field, whatever it is, decays, and its energy is converted into a blisteringly hot soup of particles. This process, called reheating, floods the universe with quarks, antiquarks, gluons, electrons, positrons, neutrinos, and photons. The temperature after reheating is estimated at around 10 to the 27 Kelvin. The universe is a plasma, a churning ocean of matter and energy so hot that particles are created and destroyed billions of times per second. Now, something deeply strange is happening. The universe is producing matter and antimatter in almost, but not quite, equal amounts. For every billion antiparticles, the cosmos produces 1,000,000,001 particles. One extra particle per billion. That tiny asymmetry, that 1 part in a billion surplus, is the only reason anything exists. Because what happens next is annihilation. Matter meets antimatter. They cancel each other out. Energy, gone. Symmetry restored. Except for that stubborn, blessed surplus. The technical term is baryogenesis, and it is one of the great unsolved problems in physics. We know the asymmetry exists because we exist. We can measure it. For every proton in the universe today, roughly 1 billion photons of the cosmic microwave background serve as tombstones for the annihilated matter-antimatter pairs. But why the asymmetry exists, what mechanism in the laws of physics preferentially produces 1 extra quark per billion, remains one of the deepest mysteries in science. The Soviet physicist Andrei Sakharov, the same man who designed the Soviet hydrogen bomb and later won the Nobel Peace Prize for human rights activism, laid out the 3 conditions necessary for baryogenesis in 1967. You need baryon number violation, you need C and CP symmetry violation, and you need departure from thermal equilibrium. The standard model of particle physics satisfies all 3, but not by enough. The asymmetry it predicts is far too small to explain what we observe. Something else is going on. We just do not know what. At about 10 to the minus 12 seconds, the electroweak force finally splits into the electromagnetic force and the weak nuclear force. This is the last of the great symmetry-breaking events, and it is associated with the Higgs mechanism. The Higgs field, which permeates all of space, acquires a non-zero value, and particles that interact with it gain mass. The photon, which does not interact with it, remains massless and will carry light across the universe forever. The W and Z bosons, which mediate the weak force, become heavy and sluggish. In 2012, the Large Hadron Collider at CERN confirmed the existence of the Higgs boson, nearly 50 years after Peter Higgs and several other theorists predicted it. The discovery was front-page news worldwide. Higgs himself, a notoriously shy man who had been largely forgotten by the mainstream, was reportedly found weeping quietly in the corridor outside the lecture hall. When asked what the discovery meant to him, he said simply, "It is very nice to be right." British understatement at its most cosmic. By 1 microsecond after the Big Bang, the universe has cooled enough for quarks to be confined into hadrons, protons, and neutrons. This transition, called the QCD phase transition, marks the end of the quark-gluon plasma era and the birth of the composite particles that will eventually form the nuclei of atoms. The strong force, the most powerful of the 4 fundamental forces, locks quarks into permanent imprisonment. No free quark has ever been observed in nature, and if our theories are correct, none ever will be. At 1 second after the Big Bang, the temperature drops to about 10 billion Kelvin, and neutrinos decouple from the rest of matter. These ghostly particles, nearly massless and barely interacting with anything, stream freely through the cosmos from this moment onward. They are still streaming. Right now, roughly 65 billion neutrinos from the sun pass through every square centimeter of your body every second, and you feel absolutely nothing. They are the universe's most antisocial particles, and they have been traveling unbothered since the cosmos was 1 second old. Also, at about 1 second, something critical happens to antimatter. The temperature drops below the threshold for producing new electron-positron pairs. The remaining positrons find their electron partners and annihilate. The light from this final annihilation joins the growing sea of photons. When the carnage is over, Only the surplus electrons, those 1 in a billion survivors, remain. Matter has won, not by strength or by right, but by the slimmest statistical margin imaginable. The universe's most consequential coin flip. If that asymmetry had been zero, if matter and antimatter had been produced in exactly equal quantities, the universe would contain nothing but radiation. No prótons, no neutrons, no átomos, no stars, no planetas, no chemistry, no biology, no consciousness. Just an ever-expanding, ever-cooling bath of photons. A universe of pure light and absolute emptiness. It would have been elegant, symmetrical, and perfectly dead. Instead, we got this magnificent, broken, lopsided mess. Lucky us. By the time the universe is 10 seconds old, it has already established the fundamental architecture of physical law. Gravity, electromagnetism, the strong force, the weak force, all separated, all operational. The Higgs field has given mass to the particles that need it. Quarks are locked inside protons and neutrons. Neutrinos are streaming freely into the void. The electromagnetic radiation field is blazingly intense. And in the turbulent, superheated plasma that fills all of space, conditions are about to become perfect for the next act. Nuclear fusion on a cosmic scale. Let us pause here and consider the sheer compressed drama of what we have just witnessed. In the time it took you to listen to this chapter, roughly 15 minutes, we covered approximately the first 10 seconds of cosmic history. 10 seconds. In those 10 seconds, the universe inflated from quantum scales to cosmic ones. The four forces of nature differentiated. Matter defeated antimatter by a margin of 1 in a billion, and the basic building blocks of all future atoms were forged. More happened in those 10 seconds than will happen in the next 10 trillion years. And yet, in a very real sense, nothing has been built yet. The universe at 10 seconds old is pure potential. Protons and neutrons exist, but they have not combined into nuclei. Electrons exist, but they have not been captured by atoms. The cosmos is a screaming, opaque fog of radiation and particles, too hot for chemistry, too dense for light to travel more than a few centimeters. It is a furnace, and it is about to become the most important furnace in history. The universe is 3 minutes old. It has already survived its own birth, inflated to cosmic proportions, sorted out its fundamental forces, and witnessed the annihilation of nearly all of its matter and antimatter. And now, in a narrow window of temperature and density that will last exactly 17 minutes, it is about to do something it will never do again. It is about to become a thermonuclear reactor the size of the observable universe. This is Big Bang nucleosynthesis, BBN for those who value their syllables. It is the process by which the first atomic nuclei were forged from the raw protons and neutrons left over after the core confinement era. Before BBN, the universe contains only free protons and free neutrons, swimming in a bath of photons, electrons, positrons, and neutrinos. After BBN, it will contain the nuclei of hydrogen, helium, and a smattering of lithium. The periodic table, such as it is, will have its first 3 entries. Let us talk about the raw materials. At the onset of nucleosynthesis, the universe contains roughly 7 protons for every 1 neutron. This ratio is critically important, and it was set by the interplay of the weak nuclear force and the cosmic expansion rate during the first second of existence. Neutrons are slightly heavier than protons, and free neutrons are unstable, decaying into protons with a half-life of about 10 minutes. So the clock is already ticking. The universe has to build its nuclei before its neutrons decay away. At about 1 minute after the Big Bang, the temperature drops to around 1 billion Kelvin, roughly 60 times hotter than the core of the Sun. This is still absurdly hot by any terrestrial standard, but it is cool enough for the first nuclear reactions to begin. Protons and neutrons start fusing. The first nucleus to form is deuterium, a hydrogen isotope with 1 proton and 1 neutron. Deuterium is the stepping stone to everything else, and it forms easily. Too easily, in fact. It also breaks apart easily. This is the deuterium bottleneck, and it is one of the most important traffic jams in cosmic history. At temperatures above about 900 million Kelvin, photons in the radiation bath carry enough energy to blast deuterium nuclei apart as fast as they form. So even though protons and neutrons desperately want to fuse, they cannot hold on to each other long enough to build anything heavier. The universe has to cool below this threshold before nucleosynthesis can proceed in earnest. It is like trying to build a sandcastle in a hurricane. At roughly 3 minutes after the Big Bang, the temperature drops below the deuterium bottleneck, and suddenly, all those frustrated nuclear reactions happen at once. Deuterium survives long enough to fuse with more protons and neutrons, forming tritium, 1 proton, 2 neutrons, and helium-3, 2 protons, 1 neutron. These intermediate nuclei then rapidly combine to form helium-4, 2 protons, 2 neutrons, the second most abundant element in the universe. It is beautifully, almost suspiciously efficient. Helium-4 is a remarkably stable nucleus. Its 4 nucleons are arranged in a configuration of exceptional binding energy, making it the terminus of most BBN reaction chains. Nearly every available neutron gets locked up in helium-4. The math is elegant. 7 protons to 1 neutron means that for every 16 nucleons, 14 protons and 2 neutrons, 1 helium-4 nucleus forms, consuming 2 neutrons and 2 protons, leaving 12 free protons. This produces a helium mass fraction of about 25%. Observe the universe today, and that is exactly what we find. This agreement between prediction and observation is one of the great triumphs of Big Bang cosmology. The primordial helium abundance was first predicted by Ralph Alpher and Robert Herman in 1948, in a paper that also predicted the existence of the cosmic microwave background. Their advisor, George Gamow, famously added the name of physicist Hans Bethe to the paper solely, so the author list would read Alpher, Bethe, Gamow, upon on the first 3 letters of the Greek alphabet. Physicists, it must be said, have a very particular sense of humor. Beyond helium-4, nucleosynthesis produces trace amounts of other light elements. Lithium-7, with 3 protons and 4 neutrons, is forged in tiny quantities. Beryllium-7 is created but quickly decays. A minuscule amount of deuterium survives without being fused further, and this leftover deuterium is actually one of the most powerful tools in observational cosmology because its abundance is exquisitely sensitive to the density of ordinary matter in the universe. In fact, the deuterium abundance is how we know, to remarkable precision, that ordinary baryonic matter makes up only about 5% of the total energy budget of the universe. 5%. Everything you have ever seen, touched, tasted, or measured, every star, every planet, every human body, every speck of dust, is composed of the universe's rounding error. The other 95% is dark matter and dark energy, invisible, untouchable, and deeply, almost personally, insulting to anyone who thought they were studying the majority of reality. But notice what is missing from the products of BBN. Carbon, nitrogen, oxygen, iron, gold, every element heavier than lithium. The universe, in its first 20 minutes, forges a periodic table with only 3 entries. Everything else, every atom of carbon in your DNA, every atom of oxygen you breathe, every atom of iron in your blood, will have to wait for stars to be born, live, and die. The cosmos cannot build complexity from its initial fire. It needs time, billions of years of it. There's a beautiful reason for this gap. To fuse helium into carbon, you need to combine 3 helium-4 nuclei simultaneously in what is called the triple alpha process. This reaction is extraordinarily unlikely under BBN conditions because the universe is expanding too fast and cooling too quickly for 3 body collisions to occur with sufficient frequency. You need sustained, stable, high-temperature environments to make carbon. You need stellar cores, and stellar cores do not exist yet. Will not exist for another 200 million years. By 20 minutes after the Big Bang, nucleosynthesis is over. The universe has cooled below the temperature required for any further nuclear fusion. The window has closed permanently. In those 17 minutes, from roughly 3 minutes to 20 minutes post-bang, the cosmic reactor has converted about 25% of its baryonic mass into helium, left about 75% as hydrogen, and produced trace amounts of deuterium, helium-3, and lithium-7. That is it. That is the universe's opening chemical inventory. Think about the absurd precision of this cosmic alchemy. If the universe had expanded slightly faster, the density would have dropped too quickly for nucleosynthesis to produce enough helium. If it had expanded slightly slower, too much helium would have formed, leaving insufficient hydrogen to fuel future stars. If the strong nuclear force had been fractionally stronger, all hydrogen would have fused into helium. If fractionally weaker, deuterium would not hold together and no heavier elements could ever form. The physicist Fred Hoyle, who ironically coined the term Big Bang as a dismissive joke on a BBC radio program in 1949, was among the first to recognize the eerie precision of nuclear physics. The strong force coupling constant, the resonance levels of carbon-12, the mass difference between protons and neutrons. Change any of these by a few percent, and you get a universe incapable of producing complex chemistry. Hoyle called it a monstrous series of accidents. He was not entirely sure it was accidental. After nucleosynthesis ends, the universe enters a long, slow cooling phase. It is still incredibly hot, hundreds of millions of Kelvin, and it is still opaque. Photons cannot travel more than a short distance before scattering off free electrons. The cosmos is a brilliant, featureless fog. No structure, no stars, no galaxies. Just an expanding, cooling soup of hydrogen nuclei, helium nuclei, free electrons, and photons, all tangled together in a state physicists call radiation-dominated. Radiation-dominated means exactly what it sounds like. The energy density of the universe is governed not by matter, but by light. Photons outnumber baryons by roughly 1 billion to 1, and they carry the majority of the energy. Matter is a contaminant, a rounding error in a cosmos ruled by radiation. But matter is patient. As the universe expands, radiation dilutes faster than matter. Photons lose energy as their wavelengths stretch with the expansion of space. Matter does not. Slowly, inexorably, the balance will shift. While we wait for that shift, let us appreciate the universe at 20 minutes old. It is homogeneous, isotropic, and featureless, the same in every direction and at every point. It has no landmarks, no structure, no variation beyond those tiny primordial density fluctuations from inflation. It is, to put it bluntly, boring. Spectacularly, magnificently boring. The most eventful 20 minutes in history have produced a cosmos that looks exactly the same everywhere you look. The interesting part, paradoxically, will require patience. About 47,000 years after the Big Bang, the transition occurs. The energy density of matter overtakes the energy density of radiation. The universe becomes matter-dominated. This is not a dramatic event. No explosions, no phase transitions. Just a quiet crossing of curves on a cosmologist's graph. But it means that gravity, which acts on matter far more effectively than on radiation, now has the upper hand. The tiny density fluctuations seeded by inflation can begin to grow. Gravity starts to build. Dark matter, in particular, begins to clump. Unlike ordinary baryonic matter, dark matter does not interact with photons. It does not feel radiation pressure. So while ordinary matter is still trapped in the photon fog, unable to collapse because every time it tries, radiation pressure blows it apart, dark matter quietly begins to gather itself into gravitational wells. It forms halos, wispy clouds of invisible mass that will eventually serve as the seeds around which galaxies will assemble. The universe's invisible architect has begun its work. But for now, the universe is still opaque, still a fog, still waiting. It will wait for another 330,000 years, cooling steadily, expanding relentlessly, until the temperature drops to about 3,000 Kelvin, cool enough for electrons to be captured by atomic nuclei for the first time. When that happens, when atoms form and the photons are finally set free, the universe will release a wall of light visible to this day. The fog will lift, and then, for a very long time, there will be nothing but darkness. 380,000 years after the Big Bang, the universe performs a magic trick. It goes from opaque to transparent in, cosmologically speaking, the blink of an eye. For all of the preceding history, photons have been trapped, scattered endlessly off free electrons like billiard balls in an infinite, superheated fog. But now the temperature has dropped to about 3,000 Kelvin, and something new becomes possible. Electrons slow down enough to be captured by hydrogen and helium nuclei. For the first time, atoms form. This event is called recombination, which is, frankly, a terrible name, since the electrons and nuclei have never been combined before. They are combining for the first time. Physicists named it in analogy to laboratory plasma physics, where ionized gas recombines into atoms, and the name stuck because physicists are excellent at equations and terrible at naming things. Regardless of what you call it, the consequences are staggering. With free electrons now bound inside atoms, photons suddenly have nothing to scatter off. The fog lifts. Light, imprisoned since the first microseconds of creation, is suddenly free to travel across the universe unimpeded. And travel it does. Those photons, released in a single epoch of cosmic transparency, are still traveling today. They're the oldest light in existence, and we call them the cosmic microwave background, or CMB. When you tune an old television to a dead channel and see static, about 1% of that noise is the CMB. You're watching the birth cry of the universe. The CMB was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey who were trying to calibrate a sensitive microwave antenna and kept picking up a persistent, unexplained background hiss. They cleaned pigeon droppings off the antenna. They pointed it in every direction. The hiss remained. It was coming from everywhere, equally, at every hour of every day. It took a phone call to Princeton physicist Robert Dicke for them to realize they had stumbled upon the most important signal in cosmology. Dicke, upon hearing the news, reportedly turned to his colleagues and said, "Boys, we've been scooped." His team at Princeton had been building their own detector to search for exactly this radiation, predicted 2 decades earlier by Alpher, Hermann, and Gamow. Penzias and Wilson won the 1978 Nobel Prize in Physics. Gamow, who died in 1968, received nothing. The history of science is littered with such ironies. The universe does not care who finds its secrets first, and the Nobel Committee, apparently, does not always either. The CMB has a temperature today of 2.725 Kelvin, just a few degrees above absolute zero. It has been cooling for 13.8 billion years, its photons stretching with the expansion of space from the visible wavelengths they were emitted at a warm, orange glow into the microwave portion of the electromagnetic spectrum. If you could see in microwaves, the entire sky would glow uniformly in every direction. It is the most perfect blackbody spectrum ever measured, matching the theoretical prediction to better than 1 part in 10,000. The COPE satellite, launched in 1989, made the first precise measurement of this spectrum, and when John Mather presented the results in American Astronomical Society meeting in January 1990, the audience gave him a standing ovation. It was the most perfect blackbody ever observed in nature, and it confirmed beyond any reasonable doubt that the universe was once in a hot, dense, equilibrium state. The Big Bang was real. Mather shared the 2006 Nobel Prize for the discovery. But the CMB is not perfectly uniform. It is almost uniform, and that almost is everything. Tiny temperature fluctuations, deviations of about 1 part in 100,000, ripple across the microwave sky. These fluctuations, first detected by COBE and later mapped in exquisite detail by WMAP and Planck, correspond to the primordial density variations seeded by quantum fluctuations during inflation. They're the DNA of cosmic structure. Every galaxy, every void, every supercluster traces its ancestry to these faint ripples in the oldest light. After recombination, the universe enters a period that cosmologists, with characteristic poetry, call the Dark Ages. No stars exist. No galaxies exist. The cosmos is filled with neutral hydrogen and helium gas, transparent to the CMB photons that are already sailing away, but producing no new light of its own. It is, in every meaningful sense, dark. Not the comfortable darkness of a night sky studded with stars, but a true, absolute, all-encompassing darkness. The universe, after the birth of its first light, goes silent. This silence will last for roughly 200 million years. 200 million years of nothing. No thermonuclear reactions. No electromagnetic emissions beyond the fading CMB. No chemistry more complex than simple hydrogen molecules forming in the cooling gas. Just darkness, expanding and cooling in every direction forever. If you had been present during the Dark Ages, assuming you could survive the vacuum and the cold, you would have seen absolutely nothing, not even your own hand in front of your face. 200 million years. Let that timescale sink in. The entirety of human civilization, from the first cave paintings to this documentary, spans about 40,000 years. The age of dinosaurs lasted 186 million years. The Dark Ages lasted longer than the reign of the dinosaurs. For longer than any complex animal has ever existed on Earth, the universe contained nothing but cooling gas in an expanding void. Patience, it turns out, is the universe's most defining characteristic. But the darkness is not idle. Gravity, the gentlest and most patient of forces, is working. During the Dark Ages, the tiny density fluctuations imprinted by inflation are slowly amplifying. Regions with slightly more matter than average exert slightly more gravitational pull, attracting surrounding matter, growing denser, attracting more. It is a positive feedback loop operating on cosmological timescales, and its primary building material is not the ordinary hydrogen and helium gas that will one day form stars. It is dark matter. Dark matter, comprising about 85% of all matter in the universe, has a crucial advantage over ordinary baryonic matter. It does not interact with light. It does not feel radiation pressure. While ordinary matter during the pre-recombination era was trapped in a tight embrace with photons, unable to collapse because radiation pressure kept blowing it apart, dark matter was free to start clumping immediately after matter-radiation equality. It had a 330,000-year head start in building gravitational structure. The result is that by the time the Dark Ages begin, dark matter has already formed a network of filaments, sheets, and halos throughout the cosmos. Think of it as invisible scaffolding, a three-dimensional web of gravitational potential wells, stretching across the entire observable universe. This is the cosmic web, and everything visible, every galaxy, every cluster, every star you will ever see in any telescope will form along its strands and at its nodes. Dark matter built the stage. Ordinary matter will perform the play. After recombination, ordinary matter is finally free from radiation pressure. Neutral hydrogen and helium gas begins to fall into the gravitational wells prepared by dark matter. It accumulates in the dark matter halos, pools at the centers of the densest knots, and starts to compress. Compression heats the gas. As it falls inward, gravitational potential energy converts to thermal energy. The gas glows faintly in infrared, invisible to the naked eye, but detectable, in principle, to future telescopes designed to see through cosmic time. This process of gas accretion is not smooth or gentle. The gas falling into dark matter halos does not settle peacefully. It collides with itself, generates shock waves, fragments, and turbulence. Angular momentum causes some of it to spiral into rotating disks. Cooling mechanisms, primarily the radiation of energy by hydrogen molecules, allow the densest regions to lose heat and collapse further. It is a complex, chaotic, multi-scale process that modern supercomputers can only approximate. The universe does not do simple. Let's talk about the role of hydrogen molecules, H2, in this drama. Atomic hydrogen, a single proton with a single electron, is actually quite bad at cooling. It can only radiate energy efficiently at temperatures above about 10,000 Kelvin. At the lower temperatures found in collapsing gas clouds during the Dark Ages, molecular hydrogen, two hydrogen atoms bonded together, becomes the primary coolant. H2 can radiate infrared photons at temperatures as low as a few hundred Kelvin, allowing the gas to shed heat and continue collapsing. Without molecular hydrogen, the first stars might never have formed, or they might have formed much later, much differently, with consequences for the entire subsequent history of the cosmos. The chemistry of a two-atom molecule, the simplest molecule possible, turns out to be one of the most important chemical reactions in the history of the universe. Grand effects from humble causes. The cosmos, it seems, has a taste for irony. As the Dark Ages progress, the densest regions of gas continue to collapse. Dark matter halos grow through mergers, small ones combining to form larger ones in a hierarchical process called bottom-up structure formation. The gas within these halos fragments into smaller and smaller clumps, each one contracting, heating, and radiating away energy through molecular hydrogen cooling. The densest, most compact clumps reach temperatures of a few thousand Kelvin and densities millions of times greater than the cosmic average. Inside the very densest of these collapsing gas clouds, conditions are approaching a threshold. The temperature is climbing toward 10 million Kelvin. The pressure is becoming enormous. Hydrogen nuclei, protons, are being driven closer and closer together. The Coulomb barrier, the electromagnetic repulsion between positively charged protons, is the only thing preventing fusion. But at these temperatures, quantum tunneling begins to overcome even that barrier. The stage is set for ignition. We are approaching the end of the Dark Ages now. 200 million years of silence, of patient gravitational accumulation, of invisible architecture being built in the void. The universe has been holding its breath, and deep inside a collapsing cloud of primordial hydrogen, in a dark matter halo somewhere in the young cosmos, the temperature has finally reached the threshold. Nuclear fusion is about to ignite. A star is about to be born. The first star, and with it, everything changes. Somewhere in the young universe, roughly 200 million years after the Big Bang, a cloud of primordial hydrogen has been collapsing for millions of years. It has fragmented, contracted, and heated under its own gravity. And now, at its very center, where the density and temperature are highest, protons are being forced together with enough energy to overcome their electromagnetic repulsion. Hydrogen fuses into helium. Energy is released. Light is emitted. For the first time since the cosmic microwave background, the universe produces new photons. A star is born. This is not a star like our sun, not even close. The first stars, called population 3 stars by astronomers using a classification system that, in true astronomical fashion, counts backwards, are utterly unlike anything in the modern universe. They form from gas that contains no elements heavier than lithium. No carbono, no oxygen, no aero, no dust. Just hydrogen and helium, the raw output of Big Bang nucleosynthesis. And this chemical purity has dramatic consequences for their size, luminosity, and fate. Without heavy elements, the gas cannot cool efficiently. In a modern universe, elements like carbon and oxygen act as powerful coolants, radiating energy and allowing gas clouds to fragment into many small, dense cores, each one forming a relatively modest star. But in the primordial universe, with only molecular hydrogen for cooling, the gas stays hot. Hot gas resists compression. It takes more mass to overcome the thermal pressure. The result, the first stars are big. Grotesquely, absurdly, catastrophically big. Current models suggest that population 3 stars had masses ranging from about 10 to over 1,000 times the mass of the Sun. Some may have exceeded 1,000 solar masses, making them the most massive stars to ever exist. By comparison, the most massive stars in the modern universe top out at about 200 to 300 solar masses. These primordial giants would have been blindingly luminous, emitting millions of times more energy than our Sun, with surface temperatures exceeding 100,000 Kelvin, hot enough to glow in the ultraviolet and even soft X-ray spectrum. Imagine one of these monsters, a star so massive that its core burns through hydrogen at a ferocious rate, its surface so hot that it emits radiation primarily in ultraviolet wavelengths invisible to the human eye. If you could see one from a safe distance, which, given its radiation output, would need to be a very safe distance indeed, it would appear as a searing blue-white point of light in an otherwise completely black universe. One star, one light, in an infinite darkness that has lasted 200 million years. That is cosmic dawn. But it is not one star. It is thousands, then millions, igniting across the cosmos in a cascading chain of gravitational collapse. Dark matter halos everywhere are reaching the mass threshold where their gas can cool and condense. Cosmic dawn is not a single sunrise, but a galaxy-spanning swarm of ignitions, each one a population 3 star blazing into existence, each one flooding its surroundings with ultraviolet radiation so intense it begins to tear apart the very atoms of the surrounding gas. This brings us to reionization, one of the most dramatic phase transitions in cosmic history. Since recombination, 380,000 years after the Big Bang, the hydrogen gas filling the universe has been neutral, each atom consisting of one proton orbited by one electron. But the ultraviolet radiation pouring out of the first stars is energetic enough to strip electrons from hydrogen atoms, reionizing them. Around each star, a bubble of ionized gas expands outward into the neutral intergalactic medium. The fog is being burned away, star by star. As more stars form and more bubbles expand, they begin to overlap. Imagine a vast, dark ocean of neutral hydrogen, and scattered throughout it, brilliant points of light, each one surrounded by an expanding sphere of transparency. At first, the spheres are isolated, lonely islands of clarity in an opaque sea. But as they grow and multiply, they begin to merge. The bubbles connect. The transparent regions link up. The neutral hydrogen between them is caught in a pincer of radiation and ionized from all sides. This process, the epoch of reionization, takes several 100 million years to complete. Current estimates place its midpoint at around 600 to 800 million years after the Big Bang, with full reionization achieved by roughly 1 billion years. The universe transitions from an opaque, neutral state to the transparent, ionized state we observe today. The James Webb Space Telescope, launched in December 2021, was specifically designed, among other goals, to study this epoch, peering back in time to observe the first galaxies and the reionization process in progress. JWST has not disappointed. In its first years of operation, it has revealed galaxies at redshifts exceeding 13, placing them within the first 400 million years after the Big Bang. Some of these galaxies are surprisingly massive, surprisingly bright, and surprisingly mature, challenging our models of early galaxy formation. The universe, it seems, got its act together faster than we expected. The first structures assembled more quickly, The first stars formed more prolifically, and the first heavy elements were produced more abundantly than our pre-JWST models predicted. But let us return to the first stars themselves, because their stories are not long ones. Population 3 stars are profligate with their fuel. A star of 100 solar masses burns through its hydrogen in about 2 to 3 million years. By comparison, our Sun has been burning for 4.6 billion years and is only halfway through its supply. These first stars live fast, burn bright, and die young, and their deaths are among the most violent events in the post-Big Bang universe. When a population 3 star of moderate mass, say 15 to 40 solar masses, exhausts its nuclear fuel, its core collapses under gravity in a fraction of a second. The infalling material rebounds off the newly formed neutron core, generating an outward propagating shock wave that tears the star apart. This is a core collapse supernova, and at its peak, it can briefly outshine an entire galaxy of hundreds of billions of ordinary stars. The explosion disperses the star's outer layers into space, and with them, the heavy elements forged in its core during its brief, furious life. 4 stars in the range of roughly 140 to 260 solar masses, something even more extreme happens. The cores of these stars become so hot that photon energies exceed the threshold for pair production. High-energy gamma rays spontaneously convert into electron-positron pairs. This drains the star of radiation pressure, the very thing holding it up against gravity. The core contracts, nuclear burning intensifies catastrophically, and the entire star detonates in a pair instability supernova. Nothing is left behind. No neutron star, no black hole. The star annihilates itself completely. A pair instability supernova releases roughly 100 times more energy than a standard core collapse event. It scatters tens of solar masses of heavy elements into the surrounding gas. Carbon, oxygen, silicon, iron, elements that did not exist anywhere in the universe before this moment, are flung into the intergalactic medium at thousands of kilometers per second. This is cosmic seeding, the first injection of chemical complexity into a universe that has, until now, known only hydrogen and helium. For the very most massive population 3 stars, those exceeding roughly 260 solar masses, the pair instability is so extreme that the core collapses directly into a black hole before the explosion can disrupt the star. These behemoths may collapse silently, swallowing themselves whole without so much as a flash of light. They become the seeds of the supermassive black holes that will eventually anchor every major galaxy, growing over billions of years through accretion and mergers into the multi-billion solar mass monsters we observe at the centers of galaxies today. Let's linger on this for a moment. The supermassive black hole at the center of the Milky Way, Sagittarius A star, contains the mass of 4 million suns. The black hole at the center of the galaxy M87, famously photographed by the Event Horizon Telescope in 2019, contains 6.5 billion solar masses. These unimaginable objects may trace their lineage back to the deaths of the very first stars. The seeds were planted at cosmic dawn. They have been growing ever since. The death of the first stars does something transformative to the universe's chemistry. The gas that forms the next generation of stars, population 2, is no longer pristine. It contains trace amounts of carbon, oxygen, and other heavy elements, what astronomers misleadingly call metals, a term that in astronomical usage means anything heavier than helium. These metals change everything. They allow gas to cool more efficiently, fragment into smaller pieces, and form smaller, longer-lived stars. Stars like our Sun become possible only because previous stars died. The oldest surviving stars in the Milky Way, found in the galactic halo and in ancient globular clusters, are population 2 stars. They formed roughly 12 to 13 billion years ago, within the first billion years after the Big Bang. Their spectra show extremely low but non-zero abundances of heavy elements. the chemical fingerprint of the population 3 stars whose supernovae enriched the gas from which they formed. These ancient stars are living fossils, carrying in their atmospheres the ashes of the first generation, a chemical memory of cosmic dawn. No confirmed population 3 star has ever been observed. They are too distant, too faint, and they died too long ago. But we infer their existence from the chemical signatures they left behind, from the reionization of the intergalactic medium, and from theoretical models of structure formation. JWST may eventually detect their light, or the light of their supernovae, redshifted across 13 billion years of cosmic expansion into the infrared. Finding a population 3 star, or its direct chemical fingerprint, remains one of the great quests of observational astronomy. There is something profoundly moving about the fate of the first stars. They were born into absolute darkness, the only lights in an infinite void. They burned with a ferocity the modern universe can scarcely produce. And they died young, violently, scattering their remains across space so that future generations of stars, planets, and eventually living things could form from their ashes. Every carbon atom in your body was forged in the nuclear furnace of a star that died before the sun was born. You are quite literally stardust. But more than that, you are the descendant of monsters. As the first generation of stars dies, the universe is irrevocably changed. It is no longer a pristine sea of hydrogen and helium. It is chemically enriched, gravitationally structured, and flooded with radiation. The dark ages are over. The cosmic dawn has broken. And in the wreckage of the first stellar generation, in the expanding shells of supernova remnants and the growing halos of dark matter, the raw materials and gravitational conditions are assembling for the next great act of creation, the birth of galaxies. But galaxies are not gentle things. They are not born quietly in a night. They are assembled through collisions, mergers, and acts of gravitational cannibalism that dwarf anything the first stars could produce. The next era of cosmic history is one of construction on a staggering scale. As dark matter halos merge, gas falls into ever deeper gravitational wells, and supermassive black holes at galactic centers begin to feed. The universe is about to build kingdoms. And kingdoms, as history will teach us again and again, are built through violence. The first stars lit the fuse. Now gravity builds the bomb. In the aftermath of cosmic dawn, as the first generation of stars lives and dies across the young universe, dark matter halos continue to grow, merge, and deepen. Gas pours into these gravitational wells from the surrounding intergalactic medium. And within those wells, enriched now by the ashes of dead population 3 stars, a new kind of structure begins to take shape. Not individual stars, not clusters, something far larger. Galaxies. A galaxy is not born in a single event. It is assembled piece by violent piece over hundreds of millions of years. The process is called hierarchical merging, and it works exactly like it sounds. Small dark matter halos, each containing a few million solar masses of gas and a scattering of early stars, collide and merge into larger halos. Those merge into larger ones still, and so on, building complexity through collision, like a snowball rolling downhill through increasingly chaotic terrain. The first proto-galaxies are small, irregular, and chaotic. They bear little resemblance to the elegant spirals and massive ellipticals of the modern universe. Think of them as cosmic construction sites, messy, violent, full of raw materials and frantic activity. Star formation within these early structures is intense, fueled by vast reservoirs of cold gas falling inward. Supernovae explode constantly, injecting energy and heavy elements back into the gas, driving turbulent winds that blow material out of the shallow gravitational wells of the smallest galaxies. This feedback cycle, stars forming, living, dying, and enriching the gas from which the next generation forms, is the engine of galactic chemical evolution. Each generation of stars is slightly richer in heavy elements than the last. The first generation forged only the lightest metals. The second incorporated those metals, burned hotter and more efficiently, and forged heavier ones in turn. It is stellar recycling on a cosmic scale, and it is still happening today. The iron in your blood has been through at least 2, possibly 3 stellar furnaces. By about 500 million years after the Big Bang, the first recognizable galaxies have assembled. They are small by modern standards, perhaps 1 billion solar masses, compared to the Milky Way's roughly 2 trillion. But they are galaxies nonetheless, gravitationally bound collections of stars, gas, dust, and dark matter, orbiting a common center. Some already show hints of rotation. Some are undergoing mergers, their stars flung into chaotic orbits by gravitational tidal forces. The cosmic zoo is beginning to populate. And at the centers of the most massive early galaxies, something ominous is growing. The black hole seeds planted by the deaths of the first stars, those collapsed remnants of population 3 giants, are feeding. Gas falling into galactic centers spirals into accretion disks around these black holes, heating to millions of degrees through friction and compression. As the gas falls past the point of no return, the event horizon, it is lost forever. But before it crosses that threshold, it radiates a staggering amount of energy. These feeding black holes produce the most luminous objects in the universe, quasars. A quasar, short for quasi-stellar radio source, is a supermassive black hole accreting matter so furiously that the energy released by its accretion disk outshines the entire galaxy around it by factors of 100 or 1,000. Some quasars are so bright they can be detected from across the observable universe. Beacons of gravitational gluttony visible at distances of 13 billion light-years. The first quasars were discovered in the early 1960s, and they baffled astronomers completely. Martin Schmidt at Caltech identified the first one, 3C273, in 1963, recognizing that its bizarrely shifted spectral lines corresponded to a redshift so large the object had to be billions of light-years away. If it was that far away and still that bright, it had to be producing more energy than any known physical process could explain. The answer, a supermassive black hole converting matter into energy with terrifying efficiency, took years to work out. The efficiency is what makes black hole accretion so extraordinary. Nuclear fusion, the process that powers stars, converts about 0.7% of the rest mass energy of hydrogen into light and heat. Black hole accretion converts between 6 and 40%, depending on the spin of the black hole. That is up to 60 times more efficient than fusion. Einstein's equation, E equals mc squared, finds its most extreme natural expression not in stellar cores, but in the swirling, superheated disks of gas spiraling into gravitational oblivion. But how do you grow a black hole from a few hundred solar masses, the remnant of a first-generation star, to several billion solar masses, the monsters observed at high redshift, in less than 1 billion years? This is one of the great unsolved problems in astrophysics. The rate at which a black hole can accrete matter is limited by radiation pressure. The very light it produces by feeding pushes incoming gas away, creating a ceiling called the Eddington limit. To reach billions of solar masses within 1 billion years, something extraordinary must happen. One possibility is super Eddington accretion, brief periods where the black hole feeds faster than the theoretical limit, perhaps through dense, clumpy gas flows that shield the incoming material from outgoing radiation. Another is direct collapse. Some primordial gas clouds may have skipped the star formation phase entirely, collapsing directly into black holes of 10,000 to 100,000 solar masses without ever igniting nuclear fusion. These direct collapse black holes would give the seeds a significant head start. A third possibility, and perhaps the most dramatic, is black hole mergers. When two galaxies collide, their central black holes eventually spiral together and merge, combining their masses in an event that shakes the fabric of space-time itself. These mergers produce gravitational waves, ripples in space-time, first predicted by Einstein in 1916 and first detected by the LIGO Observatory in September 2015. That detection of two stellar-mass black holes merging 1.3 billion light-years away won the 2017 Nobel Prize in Physics. While individual galaxies are assembling, the large-scale structure of the universe is taking shape around them. Dark matter, guided by the primordial density fluctuations from inflation, has organized itself into a vast, three-dimensional network, the cosmic web. Imagine a sponge the size of the observable universe, with dense filaments of dark matter forming the walls and junctions, and enormous voids, regions nearly devoid of matter, filling the spaces between. Galaxies form along the filaments and cluster at the nodes where filaments intersect. The cosmic web is staggering in scale. Individual filaments can stretch for hundreds of millions of light years. The voids between them span hundreds of millions of light years across, containing almost no galaxies at all. The densest nodes, where multiple filaments converge, contain galaxy clusters, gravitationally bound collections of hundreds or thousands of galaxies, embedded in a shared halo of dark matter and hot intracluster gas. Galaxy clusters are the most massive gravitationally bound structures in the universe. The Sloan Digital Sky Survey, one of the most ambitious mapping projects in the history of astronomy, has charted the positions of millions of galaxies, revealing the cosmic web in breathtaking detail. The resulting maps look eerily organic, like neural networks or biological tissue. This is not a coincidence of aesthetics. The mathematics of networks, whether they describe neurons, blood vessels, or dark matter filaments, tend to produce similar structures. The universe, at its largest scale, looks disturbingly like a brain. Along the filaments, galaxies do not simply sit still. They move, drawn by gravity, toward the densest concentrations of mass. Galaxies fall along filaments toward clusters. Clusters are drawn toward superclusters, and superclusters drift toward even larger concentrations in a phenomenon called cosmic flow. Our own Milky Way is falling toward the Virgo cluster, which is itself falling toward the Great Attractor, a gravitational anomaly in the direction of the constellation Centaurus, whose full nature remains only partially understood. In 2014, a team led by Brent Tully mapped the full extent of our home supercluster, naming it Laniakea, a Hawaiian word meaning immense heaven. Laniakea contains approximately 100,000 galaxies spanning 520 million light-years, and the Milky Way sits at its outer edge, a suburb in the outskirts of a cosmic metropolis. It is a humbling cartography. We thought we were somewhere important. It turns out we are on the edge of a structure whose existence we only confirmed a decade ago. By roughly 1 to 2 billion years after the Big Bang, the basic architecture of the observable universe is in place. The cosmic web spans the cosmos. Galaxies populate its filaments and nodes. Supermassive black holes anchor their centers. The intergalactic medium, ionized and enriched by the first generations of stars, fills the voids between filaments with a thin, hot plasma. The universe has gone from a smooth, featureless fog to a richly structured landscape of matter and energy. The construction phase is largely complete. But construction is not the same as production. The galaxies that now fill the cosmic web are factories, and their primary product is stars. Over the next several billion years, star formation will accelerate to its all-time peak, filling galaxies with hundreds of billions of new stars, forging the heavy elements that will eventually compose rocky planets, liquid oceans, and living organisms. The universe has built its kingdoms. Now it is time to fire up the furnaces. The universe hits its stride. Between 2 and 6 billion years after the Big Bang, an era astronomers call cosmic noon, the rate of star formation across the observable universe reaches its absolute peak. Galaxies are manufacturing new stars at 10 to 20 times the rate of the present-day cosmos. Every year, the universe converts hundreds of solar masses of gas into new stars. It is an age of furious, relentless creation, a cosmic industrial revolution that will never be equaled again. Why does star formation peak at this particular epoch? Because the conditions are perfect. Galaxies have accumulated vast reservoirs of cold gas from the intergalactic medium. Enough heavy elements have been produced by earlier stellar generations to enable efficient gas, cooling, and fragmentation. Dark matter halos are massive enough to sustain prolonged accretion. And galaxy mergers, which trigger violent bursts of star formation by compressing gas clouds, are occurring at their highest rate. Everything conspires to make this the most productive era in cosmic history. To understand what happens inside these stellar factories, we need to understand how a star actually works. And the answer, at its core, no pun intended, while maybe a little intended, is beautifully simple. A star is a ball of gas held in equilibrium between two opposing forces: gravity, which wants to crush it, and radiation pressure from nuclear fusion, which wants to blow it apart. As long as fusion continues, the star holds. When fusion stops, gravity wins. Every star is a temporary truce between creation and collapse. The fuel for this fusion is hydrogen, the most abundant element in the universe. In the core of a star like our Sun, where temperatures reach about 15 million Kelvin, hydrogen nuclei, protons, are fused into helium through a chain of reactions called the proton-proton chain. For protons go in, one helium-4 nucleus comes out. The mass of the helium is slightly less than the mass of the 4 protons. That missing mass, about 0.7% of the total, has been converted into energy according to Einstein's famous equation. The numbers are staggering. Every second, the Sun converts approximately 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons become energy, 3.8 times 10 to the 26 watts of luminosity, radiated in every direction. The Sun has been doing this for 4.6 billion years and has barely used half its hydrogen supply. It is the most reliable engine in the solar system, and it runs on the cheapest fuel in the universe. But not all stars burn like the Sun's stellar mass determines everything: temperature, luminosity, color, lifespan, and ultimate fate. The mass-luminosity relationship is steep. A star 10 times the mass of the Sun is not 10 times brighter. It is roughly 10,000 times brighter. This means it burns through its fuel not 10 times faster, but roughly 1,000 times faster. Massive stars live fast. A star of 50 solar masses might exhaust its hydrogen in just a few million years. The Sun will last 10 billion. At the opposite end of the scale are red dwarfs, stars with masses between about 8 and 50% of the Sun. These are the universe's misers, burning their hydrogen so slowly and so efficiently that they can last for trillions of years, far longer than the current age of the universe. No red dwarf that has ever been born has yet died of old age. They're still out there, every single one of them, the oldest and most patient objects in the cosmos. Red dwarfs outnumber all other stellar types combined. When a star like the Sun exhausts the hydrogen in its core, fusion does not simply stop. Instead, the core contracts under gravity, heats up, and hydrogen fusion continues in a shell surrounding the now inert helium core. The energy from shell burning causes the outer layers of the star to expand enormously. The star becomes a red giant, its radius swelling to perhaps 100 times its original size, its surface cooling to a deep, angry red. Our Sun will do this in about 5 billion years, engulfing Mercury, Venus, and possibly Earth. In the core of a sufficiently massive red giant, temperatures eventually reach about 100 million Kelvin, hot enough to ignite helium fusion. 3 helium-4 nuclei combine to form carbon-12 through the triple alpha process, the very reaction that was impossible during Big Bang nucleosynthesis. Fred Hoyle predicted in 1953 that carbon-12 must have a specific nuclear resonance, an excited energy state, to make this reaction efficient enough to produce the observed abundance of carbon. He was right. Without that resonance, carbon would be vanishingly rare, and so would life. Carbon, the fourth most abundant element in the universe, the backbone of every organic molecule, the element upon which all known life is based. It was forged in the cores of red giant stars through a reaction that depends on a nuclear resonance so precisely tuned that its discoverer suspected intelligent design. Hoyle, an atheist, was so disturbed by the fine-tuning that he wrote, "A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics." Even he could not quite explain it away. 4 stars of moderate mass, about 1 to 8 solar masses, the story ends with helium burning. The core eventually becomes too cool to ignite carbon fusion. The star sheds its outer layers in a beautiful, glowing shell of ionized gas called a planetary nebula, one of the most visually spectacular phenomena in astronomy. At the center, the exposed core remains, a white dwarf, roughly the mass of the sun compressed into a sphere the size of the Earth. Dense, hot, and slowly cooling, it will take billions of years to fade to black. White dwarfs are among the strangest objects in the universe. A teaspoon of white dwarf material would weigh about 5 tons on Earth. The matter is so densely packed that atoms are crushed together, their electron clouds overlapping, sustained only by a quantum mechanical effect called electron degeneracy pressure. It is not heat or radiation holding the star up. It is the Pauli exclusion principle, a rule of quantum mechanics that forbids 2 electrons from occupying the same quantum state. Physics at its most fundamental is all that stands between a white dwarf and total gravitational collapse. But for stars above about 8 solar masses, the story is far more dramatic. These massive stars do not stop at carbon. Their cores are hot enough and dense enough to ignite carbon fusion, producing neon and magnesium. Then neon burning, producing oxygen. Then oxygen burning, producing silicon. Then silicon burning, producing iron. Each stage burns faster and more furiously than the last. Carbon burning lasts about 1,000 years. Neon burning lasts about a year. Oxygen burning lasts months. Silicon burning lasts about a single day. The result is a star with an onion-like structure, concentric shells of increasingly heavy elements, each one fusing into the next, with an iron core at the center. Iron is the end of the line. Fusing iron does not release energy. It consumes it. Iron has the highest binding energy per nucleon of any element. To fuse iron into anything heavier, you have to put energy in, not take it out. The stellar furnace has produced its own poison. The fire goes cold. What happens next takes less than a second. The iron core, no longer sustained by fusion energy, collapses under its own gravity. The collapse is catastrophic. The core shrinks from roughly the size of the Earth to the size of a city in milliseconds. Protons and electrons are forced together, forming neutrons and releasing a flood of neutrinos. The infalling outer layers slam into the now incompressible neutron core and rebound. A shock wave races outward. The star explodes. This is a Type II supernova. A Type II supernova releases approximately 10 to the 46 joules of energy, most of it carried away by neutrinos. To put that in context, it is more energy than the sun will produce in its entire 10 billion year lifetime. For a few weeks, a single dying star can outshine an entire galaxy of 100 billion stars. The explosion scatters the star's outer layers, enriched with all those elements forged during its lifetime: carbon, oxygen, silicon, iron, into the surrounding interstellar medium at speeds of tens of thousands of kilometers per second. But a supernova does more than just disperse the elements the star made while alive. The explosion itself, through a process called explosive nucleosynthesis, forges elements heavier than iron. The intense neutron flux during the explosion drives rapid neutron capture. They are a process building elements far up the periodic table: silver, gold, platinum, uranium. Every atom of gold in every ring every necklace, every bar, and every vault on Earth was forged in the collapsing heart of a dying star. Precious metals are the currency of stellar death. For decades, supernovae were thought to be the primary site of our process nucleosynthesis. But in 2017, a new contender emerged. On August 17th of that year, LIGO and Virgo detected gravitational waves from the merger of two neutron stars, 130 million light-years away. Telescopes worldwide turned to observe the event, designated GW 170817, and what they saw was a kilonova, a burst of light powered by the radioactive decay of newly synthesized or process elements. The neutron star merger had forged roughly 10 Earth masses of gold and platinum in seconds. 10 Earth masses of gold, produced in a collision lasting less than 2 seconds, flung into space at a significant fraction of the speed of light. That single event rewrote textbooks. Neutron star mergers, it turns out, may be responsible for the majority of the heaviest elements in the universe, not supernovae. The gold in your jewelry was likely forged not in an exploding star, but in the violent collision of two stellar corpses, each denser than an atomic nucleus, spiraling together after billions of years of orbital decay. What remains after a supernova depends on the mass of the original star. 4 stars between roughly 8 and 25 solar masses. The core collapse produces a neutron star, a sphere about 20 kilometers in diameter, containing 1 to 2 solar masses of matter compressed to nuclear density. A teaspoon of neutron star material would weigh about 1 billion tons. Neutron stars spin rapidly, some hundreds of times per second, and those with strong magnetic fields emit beams of radiation from their poles, observed as pulsars. Pulsars were discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge, who noticed a repeating radio signal pulsing with clockwork precision every 1.337 seconds. Her advisor, Anthony Hewish, initially dismissed it. The signal was briefly nicknamed LGM-1 for Little Green Men before its true nature was understood. Hewish won the Nobel Prize for the discovery in 1974. Bell Burnell did not. The injustice has been discussed, debated, and lamented by the physics community for half a century. She has handled it with considerably more grace than the situation deserved. For the most massive stars, those above roughly 25 solar masses, even neutron degeneracy pressure cannot halt the collapse. The core crashes through every known physical barrier and becomes a stellar mass black hole, a singularity of infinite density surrounded by an event horizon from which nothing, not light, not information, not hope, can escape. The black hole inherits the angular momentum and mass of the collapsed core, typically 5 to 15 solar masses, and sits in the expanding debris field of the supernova remnant like a gravestone. And so the stellar furnace operates. Hydrogen and helium go in, and everything else comes out. Stars are the universe's alchemists, transmuting the simple products of the Big Bang into the 92 naturally occurring elements of the periodic table. Every breath you take contains oxygen forged in a massive star. Every drop of your blood contains iron from a supernova. Every circuit in every computer contains copper and silicon from stellar cores. The universe built its complexity one death at a time. Creation through destruction. Order from violence. After cosmic noon, star formation begins to decline. The cold gas that fuels it is being consumed faster than it can be replenished. Galaxies are growing more massive, but less active, transitioning from blue, star-forming spirals, to red, quiescent ellipticals. The universe is past its productive peak. It will never again create stars at the rate it did during those golden billions of years. The furnace is not extinguished, but the flame is dimming, and it will continue to dim for the rest of cosmic history. At the heart of nearly every large galaxy in the observable universe sits a monster, not a metaphorical monster, not a poetic exaggeration, A genuine, physics-defying, space-time warping monster of such extreme gravitational power that it bends reality itself into shapes that would have given Einstein nightmares. We're talking about supermassive black holes, objects containing millions to billions of solar masses, compressed into a region smaller than our solar system. They are the darkest, densest, most destructive objects in creation, and they are everywhere. The relationship between galaxies and their central black holes is one of the most surprising discoveries in modern astrophysics. The mass of a galaxy's central black hole correlates tightly with the mass of its central stellar bulge, even though the black hole typically contains less than 1% of the bulge's mass. This correlation, called the M-sigma relation, suggests that the black hole and its host galaxy grew together, each one shaping the other through feedback processes that operated across billions of years. How does a black hole, locked away at the center of a galaxy, influence structures millions of light years across? Through sheer, terrifying energy output. When a supermassive black hole actively accretes matter, it becomes what astronomers call an active galactic nucleus, or AGN. The accretion disk surrounding the black hole can reach temperatures of millions of Kelvin, emitting radiation across the entire electromagnetic spectrum: radio, infrared, visible, ultraviolet, X-ray, and gamma ray. A single AGN can outpower every star in its host galaxy combined. AGN come in a bewildering variety of flavors. Safer galaxies have relatively modest AGN, their central engines visible but not overwhelming. Quasars are the most luminous, their black holes gorging on vast quantities of gas. Blazars are quasars whose relativistic jets happen to point directly at Earth, making them appear even brighter due to relativistic beaming. Radio galaxies produce enormous lobes of radio emission, fed by jets that extend far beyond the visible boundaries of the galaxy. For decades, astronomers classified these as different objects. It turns out they're the same object, viewed from different angles. This is the AGN unified model, proposed in the 1980s and 1990s. All active galactic nuclei are fundamentally the same engine, a supermassive black hole surrounded by an accretion disk, which is in turn surrounded by a donut-shaped torus of dust and gas. What you see depends entirely on your viewing angle. Look down the jet, blazar. Look from the side, radio galaxy. Look through the torus, obscured AGN. Look at the disk, quasar. It is cosmic perspective at its most literal. The jets produced by some AGN are among the most spectacular phenomena in the universe. Collimated beams of plasma, accelerated to speeds exceeding 99% of the speed of light, shoot outward from the poles of the accretion disk along the black hole's spin axis. These relativistic jets can extend for hundreds of thousands of light years, far beyond the boundaries of the host galaxy, inflating enormous lobes of radio-emitting plasma in the intergalactic medium. The energy contained in these jets is almost incomprehensible. Hercules A, a galaxy 2 billion light-years from Earth, produces jets that span 1.5 million light-years from end to end. That is 15 times the diameter of the Milky Way. A structure of pure energy, launched from an object smaller than our solar system, stretching across a volume of space so vast that light takes 1.5 million years to cross it. The black hole at the center of Hercules A weighs roughly 2.5 billion solar masses. It has been launching these jets for tens of millions of years without pausing. But the jets are not just spectacular. They are functional. They carry enormous amounts of energy into the surrounding gas, heating it, disrupting it, and preventing it from cooling and collapsing to form new stars. This is AGN feedback. It is believed to be one of the primary mechanisms that regulate star formation in massive galaxies. Without AGN feedback, the most massive galaxies in the universe would contain far more stars than we observe. The black hole, paradoxically, prevents its host galaxy from growing too large. The destroyer is also the regulator. There are two modes of AGN feedback. In quasar mode, The black hole accretes at a high rate, producing intense radiation that drives powerful winds capable of sweeping gas out of the galaxy entirely. These outflows have been observed in numerous galaxies, with velocities exceeding 1,000 kilometers per second. In radio mode, the black hole accretes at a lower rate, but produces powerful jets that gently heat the surrounding gas, preventing it from cooling. One mode blows gas out, the other keeps it warm. Both suppress star formation. The consequences of AGN feedback are written across the galaxy population. The most massive elliptical galaxies, those at the centers of galaxy clusters, are red and dead, dominated by old, red stars with very little ongoing star formation. Their central black holes, some exceeding 10 billion solar masses, have effectively sterilized their host galaxies, heating and expelling the cold gas that would otherwise fuel new stars. These galaxies are magnificent but moribund, frozen in a state of slowly fading grandeur. The monsters at their centers kill them softly. Let us now descend to the event horizon itself, the boundary of a black hole, where physics reaches its most extreme and most unsettling. The event horizon is not a physical surface. You cannot touch it. There is no wall, no membrane, no barrier. It is a mathematical boundary, the point at which the escape velocity equals the speed of light. Cross it, and no force in the universe can bring you back. Not because something is holding you in, but because all paths through space-time, even paths that point outward, now curve inward toward the singularity. For an observer falling into a supermassive black hole, the crossing would be eerily uneventful. Tidal forces at the event horizon of a billion solar mass black hole are negligible. You would cross the boundary without feeling a thing, without any local measurement telling you that something irrevocable had just happened. The horror is purely informational. You can never return, you can never send a signal back, and you will, in a finite amount of your own time, reach the singularity. What happens there, physics cannot say. Our equations produce infinities, which is mathematics, for we have no idea. Time dilation at the event horizon is infinite. To a distant observer watching you fall in, you would appear to slow down, redden, and fade, your image stretching and dimming as light from your body struggles against the gravitational field. You would never quite disappear. Your image would linger at the horizon for eternity, growing dimmer and dimmer, redshifted beyond detection, but never quite gone. To the outside universe, you are frozen at the edge of oblivion. To yourself, you sailed right through. Two perspectives, both correct, utterly irreconcilable. In April 2019, the Event Horizon Telescope, a globe-spanning network of radio telescopes operating as a single Earth-sized instrument, produced the first direct image of a black hole shadow. The target was M87 star, the supermassive black hole at the center of the galaxy Messier 87, weighing 6.5 billion solar masses. The image, a glowing orange ring surrounding a dark central void, was simultaneously anticlimactic and profound. It looked exactly like our theories predicted. Einstein was right. Again. In 2022, the EHD followed up with an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way. At 4 million solar masses, it is far smaller than M87 star, and far more difficult to image because gas orbiting it moves so quickly that the appearance changes on timescales of minutes. The resulting image was a triumph of computational and observational astronomy, confirming that the dark, quiet center of our galaxy harbors a space-time anomaly of extraordinary power. It is sleeping for now, but it has fed before, and it will feed again. Stephen Hawking, in one of the most remarkable theoretical insights of the 20th century, demonstrated in 1974 that black holes are not entirely black. Quantum effects at the event horizon cause black holes to emit a faint thermal radiation, now called Hawking radiation. This means black holes have a temperature, they have entropy, and most astonishingly, they slowly evaporate. Over timescales that dwarf the current age of the universe, A black hole will radiate away its entire mass and vanish in a final burst of energy. Even gravity's ultimate prisons are not permanent. Hawking radiation raises what is perhaps the deepest problem in theoretical physics, the black hole information paradox. If a black hole evaporates completely, what happens to the information about everything that fell in? Quantum mechanics insists that information cannot be destroyed. General relativity says it is trapped behind the event horizon. These two pillars of physics give contradictory answers, and resolving this paradox may require a fundamental revision of our understanding of space, time, or both. Physicists have been arguing about it for 50 years. They are no closer to consensus. The monsters in the dark have shaped the cosmos more profoundly than anyone imagined. They regulate star formation. They drive galactic winds. They produce the most luminous objects in the observable universe. They warp space-time into geometries that challenge our understanding of reality itself. And they sit, patient and eternal, on any human timescale at the gravitational centers of nearly every galaxy, silent sentinels of a universe that builds its grandest structures around its most destructive objects. Destruction and creation, once again, revealed as two faces of the same cosmic coin. We have spent 4 chapters discussing the universe in general. Now it is time to get personal. Out of the hundreds of billions of galaxies in the observable universe, we are going to focus on one. Not because it is special, not because it is the largest or the brightest or the most interesting, but because it is ours. The Milky Way, a barred spiral galaxy of modest size and unremarkable position, home to somewhere between 100 and 400 billion stars, including one that happens to warm your face on a clear afternoon. The name itself is ancient. The Greeks called it Galaxias Kyklos, the Milky Circle, from a myth in which the infant Heracles, suckling at the breast of the goddess Hera, spilled her divine milk across the sky. The Romans translated it as Via Lactea. In reality, of course, the milky band of light visible on clear, dark nights is the combined glow of billions of distant stars in the galactic disk, too numerous and too faint to resolve individually with the naked eye. Galileo was the first to see them in 1610 through his telescope. He was stunned. The Milky Way was not born. It was assembled. Like all large galaxies, it is the product of billions of years of hierarchical merging, a process in which smaller galaxies collide, merge, and are absorbed into ever larger structures. The Milky Way we see today is the accumulated wreckage of dozens, perhaps hundreds, of smaller galaxies consumed over cosmic time. Their stars, their gas, their dark matter, all digested and incorporated into the structure we now call home. Our galaxy is a cannibal. The most dramatic known chapter in this cannibalistic history was revealed by the Gaia spacecraft, launched by the European Space Agency in 2013. Gaia has measured the positions, motions, and distances of nearly 2 billion stars in the Milky Way with extraordinary precision, and its data revealed something remarkable. A significant fraction of the stars in the galactic halo move in patterns that are completely inconsistent with the rest of the galaxy. They are interlopers, immigrants from a galaxy that no longer exists. That galaxy has been named Gaia Enceladus, and it collided with the young Milky Way roughly 10 billion years ago. Gaia Enceladus was a substantial dwarf galaxy, containing perhaps several hundred million stars, and its merger with our galaxy was no gentle affair. The collision scattered stars into chaotic orbits, thickened the Milky Way's disk, and triggered bursts of star formation as gas clouds compressed and fragmented. The merger fundamentally reshaped the structure of our galaxy, contributing a large fraction of the stars now found in the inner halo. We can identify former Gaia Enceladus stars because they carry a distinctive chemical fingerprint. Their elemental abundances, the ratios of iron to hydrogen, alpha elements to iron, and other diagnostic signatures differ from those of stars born natively in the Milky Way. These stars formed in a different environment, with a different star formation history, and were then deposited in our galaxy when their home was destroyed. They are archaeological evidence of a cosmic crime, witnesses preserved in orbits that still echo the violence of an ancient collision. Gaia Enceladus was not the only victim. The Milky Way has consumed numerous smaller galaxies over its history, and it is still doing so today. The Sagittarius Dwarf Elliptical Galaxy, discovered in 1994, is currently being torn apart by the Milky Way's tidal forces. Its stars are being stripped away and stretched into a long, looping stellar stream that wraps around our galaxy multiple times, like a cosmic crime scene outline. Within 1 billion years, the Sagittarius Dwarf will cease to exist as a distinct entity. Its stars will become our stars. The Magellanic Clouds, visible from the southern hemisphere as 2 fuzzy patches of light, are also interacting with the Milky Way. The large and small Magellanic Clouds are dwarf galaxies, the largest satellite galaxies of the Milky Way, and they're trailing a vast stream of neutral hydrogen gas called the Magellanic Stream that stretches across more than 200 degrees of the sky. Whether they will eventually be consumed by the Milky Way or escape after a single passage remains an active area of research. The structure of the Milky Way itself is complex and, honestly, difficult to study because we are inside it. Trying to map the Milky Way from Earth is like trying to map a forest while standing in the middle of it. But through decades of radio, infrared, and optical observations, supplemented by Gaia's revolutionary data, we now have a reasonably good picture. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years in diameter, with a central bar-shaped bulge, several major and minor spiral arms, and a diffuse halo of old stars and globular clusters extending far beyond the visible disk. The spiral arms are not rigid structures. They are density waves, regions of higher gas density that propagate through the galactic disk like sound waves through air. Stars and gas clouds orbit the galactic center at different speeds depending on their distance. But as they pass through a density wave, the enhanced gravitational pull compresses the gas, triggers star formation, and produces the bright blue, star-forming regions that delineate the arms. The arms are traffic jams in the flow of galactic material. The blue stars are the pileup. Our sun sits roughly 26,000 light-years from the galactic center, about halfway out along the disk, in a minor spur between the Sagittarius and Perseus arms, sometimes called the Orion arm or the local spur. It orbits the galactic center at about 220 kilometers per second, completing one full orbit every 225 to 250 million years, a period sometimes called a galactic year. The sun has completed roughly 18 to 20 orbits since its birth. The dinosaurs were alive only a fraction of an orbit ago. At the very center of the Milky Way, lurking behind vast clouds of obscuring dust, sits Sagittarius A star. For decades, its existence was inferred from the rapid orbits of nearby stars. Stars whipping around an invisible point at thousands of kilometers per second, their paths tracing out ellipses that pointed to a central mass of about 4 million suns compressed into a region smaller than Mercury's orbit. The team led by Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute shared the 2020 Nobel Prize in Physics for this discovery. Sagittarius A star is currently quiet, accreting an extraordinarily low rate compared to the supermassive black holes in active galaxies. It is not a quasar. It is not even a particularly active AGN. It is, by black hole standards, asleep. But evidence suggests it was not always so dormant. X-ray observations have detected light echoes from the gas clouds near the galactic center, suggesting that Sagittarius A star flared dramatically within the last few hundred years, perhaps from swallowing a stray gas cloud or an unlucky star. The galactic center is a violent, crowded, and thoroughly inhospitable environment. Within the innermost few light years, stellar densities are millions of times higher than in the sun's neighborhood. Stars orbit at relativistic speeds. Tidal forces from the black hole rip apart gas clouds. Intense radiation from hot, massive stars floods the region. It is the last place in the galaxy you would want to build a civilization, and, reassuringly, we are 26,000 light years away from it. Location, as they say, is everything. The Milky Way's halo deserves special attention. Extending far above and below the galactic disk, the halo contains some of the oldest stars in the galaxy. Metal-poor population 2 stars with ages exceeding 12 billion years. Many of these stars were born in smaller galaxies that were later consumed by the Milky Way. Others formed during the earliest episodes of star formation in the proto-Milky Way itself. They are fossils, carrying in their spectra the chemical history of a universe less than 2 billion years old. Scattered through the halo are roughly 150 globular clusters, dense, spherical collections of hundreds of thousands to millions of stars, gravitationally bound and ancient. Some globular clusters in the Milky Way are nearly as old as the universe itself. They formed during the earliest stages of galaxy assembly, and they have survived for over 12 billion years, enduring galactic collisions, tidal disruptions, and the slow evaporation of their outermost stars. They are the Milky Way's elders, silent witnesses to a history that stretches back almost to the cosmic dawn. One more character in the Milky Way story deserves mention: the dark matter halo. Extending far beyond the visible galaxy, to a radius of perhaps 200,000 to 300,000 light years, the dark matter halo contains the majority of the Milky Way's total mass, roughly 1 trillion solar masses compared to about 100 billion in ordinary matter. We cannot see it. We can only infer its presence from the rotation curve of the galaxy, the velocities of satellite galaxies, and the dynamics of stellar streams. The Milky Way is mostly invisible. The Milky Way's future has already been written, at least in broad strokes. In approximately 4.5 billion years, it will collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor, currently approaching at about 110 kilometers per second. The merger will take roughly 2 billion years to complete, reshuffling the orbits of billions of stars, triggering new bursts of star formation, and eventually producing a single, massive elliptical galaxy that astronomers have already nicknamed Milkomeda. Our spiral arms will be gone. Our neighborhood will be unrecognizable. But individual stars, including our sun if it survives, will almost certainly not collide. Galaxies are that empty. But that is a story for the deep future. For now, let us return to a specific moment, roughly 4.6 billion years ago, when the Milky Way was about 9 billion years old. In a quiet region of the galactic disk, far from the drama of the galactic center, far from any recent supernova, a cloud of gas and dust, enriched by generations of stellar death, begins to contract under its own gravity. This cloud is not special. It is not the largest or the densest or the most chemically interesting. But what it produces will change everything, at least for us. 4.6 billion years ago, in the Orion arm of the Milky Way, a molecular cloud begins to collapse. Molecular clouds are the stellar nurseries of the galaxy. Vast, cold, dense accumulations of gas and dust, mostly hydrogen and helium, but seeded with heavier elements forged in the deaths of previous generations of stars. This particular cloud spans several light years across. It is cold, perhaps 10 Kelvin, barely above absolute zero. And something, perhaps the shock wave from a nearby supernova, perhaps the passage through a spiral density wave, has disturbed its equilibrium. The evidence for a supernova trigger is tantalizing. Certain meteorites, the most ancient and pristine rocks in the solar system, contain anomalous abundances of short-lived radioactive isotopes like aluminium-26 and iron-60, isotopes that can only be produced in supernovae and that decay so rapidly they must have been incorporated into the solar system's building materials within a few million years of their creation. The Sun, it seems, may owe its existence to the death of a star that exploded in its neighborhood just before its own birth. Creation from destruction, once again. As the cloud collapses, conservation of angular momentum causes it to spin faster and flatten into a disk. Think of an ice skater pulling in their arms. The same physics operating on a scale of billions of kilometers. At the center, where the density is highest, the material compresses and heats. This central concentration is the proto-sun, a growing ball of gas that is not yet hot enough for nuclear fusion, but is steadily approaching that threshold. The disk that surrounds it is called the protoplanetary disk, or the solar nebula. And within it, the raw materials for planets are beginning to aggregate. The solar nebula is not uniform. Temperature decreases with distance from the proto-sun. In the inner regions, close to the forming star, temperatures are high enough to vaporize most volatile substances: water, methane, ammonia. Only refractory materials, metals, and silicate minerals can exist as solids. Further out, beyond a boundary called the snow line, located at roughly 2.7 astronomical units from the sun in our system, temperatures drop low enough for water to freeze into solid ice. This temperature gradient will determine the fundamental architecture of the solar system. Inside the snow line, the available solid material is limited to about 0.5% of the total disk mass: metals and silicates. The planets that form here will be small and rocky: Mercury, Venus, Earth, Mars. Beyond the snow line, the addition of water ice roughly quadruples the available solid mass. The cores of planets forming here can grow much larger, large enough to gravitationally capture the abundant hydrogen and helium gas from the surrounding disk. This is how Jupiter and Saturn, the gas giants, become so massive. Location determines destiny. Planet formation begins with dust, tiny grains of silicate and iron, each one smaller than a grain of sand, drift through the solar nebula, colliding gently and sticking together through electrostatic forces and van der Waals interactions. These aggregates grow from micrometers to centimeters to meters. But meter-sized bodies face a problem. They are large enough to experience significant aerodynamic drag from the gas in the disk, causing them to spiral inward toward the sun, but too small for gravity to hold them together during collisions. This is the meter barrier, and overcoming it is one of the great puzzles of planet formation. Somehow, through mechanisms still debated, the meter barrier is overcome. Possible solutions include streaming instabilities, where interactions between gas and dust concentrate particles into dense clumps that collapse gravitationally, or pebble accretion, where small bodies grow rapidly by sweeping up centimeter-sized pebbles from the disk. Whatever the mechanism, the result is the formation of planetesimals, rocky bodies a few kilometers across, held together by their own gravity. These planetesimals are the building blocks of planets, and they number in the billions. From this point, gravity takes over. Planetesimals collide, merge, and grow. Larger bodies have stronger gravitational pull, attracting more material and growing faster, a process called runaway accretion. Within a few million years, the swarm of billions of planetesimals has been consolidated into a few dozen planetary embryos, each one roughly the size of the Moon to Mars. These embryos continue to collide in increasingly violent impacts. The inner solar system, during this epoch, is a demolition derby of world-sized bodies, each collision releasing enough energy to melt entire planets. Meanwhile, the proto-sun has reached its ignition threshold. Roughly 100,000 years after the initial collapse began, the core temperature exceeds 10 million Kelvin and hydrogen fusion ignites. The sun is born, a T-Tauri star, young and variable, producing powerful stellar winds and ultraviolet radiation that begin to erode the protoplanetary disk from the inside out. The clock is now ticking. The gas giants must form before the disk dissipates, a process that takes roughly 5 to 10 million years. After that, no more gas giants can form, ever. Jupiter forms first, and it forms fast. Its core, roughly 10 to 20 Earth masses of rock and ice, accretes beyond the snow line where solid material is abundant. Once the core reaches a critical mass, it begins to gravitationally capture gas from the disk at an accelerating rate, a process called runaway gas accretion. Within perhaps 1,000,000 years, Jupiter grows to 318 Earth masses, becoming the dominant gravitational force in the solar system after the Sun itself. Its influence will shape the orbits and fates of every other planet. And shape them it does, in ways we are only beginning to understand. The Grand Tack hypothesis, proposed by Kevin Walsh and colleagues in 2011, suggests that Jupiter did not stay where it formed. Early in the solar system's history, Jupiter migrated inward toward the Sun, driven by interactions with the gas disk, reaching as close as 1.5 astronomical units, roughly where Mars is today. It then reversed course, tacking like a sailboat, when Saturn formed and became locked in a gravitational resonance that pulled both planets outward to their current positions. If the Grand Tack is correct, its consequences for the inner solar system were enormous. Jupiter's inward migration would have scattered and depleted the material in the Mars region, explaining why Mars is only about 1/10 the mass of Earth, a puzzle that standard accretion models struggle to resolve. It would also have stirred the asteroid belt, implanting water-rich asteroids from the outer solar system into the inner belt. And it would have truncated the inner disk, limiting the material available to form Mercury, Venus, Earth, and Mars. Saturn, Uranus, and Neptune form in the outer solar system, each with its own complex history. Saturn, like Jupiter, is a gas giant, though smaller, with its iconic ring system formed from the tidal disruption of moons, comets, or both. Uranus and Neptune are ice giants, their interiors dominated by water, methane, and ammonia ices rather than hydrogen and helium gas. Both may have formed closer to the Sun than their current positions and migrated outward during a later dynamical rearrangement, scattering icy bodies across the outer solar system in the process. That rearrangement is described by the Nice model, named after the city in France where it was developed, not a qualitative judgment, though it is in fact a Nice model, proposed by Tsiganis, Gomez, Morbidelli, and Levison in 2005. The Nice model describes a period roughly 500 to 700 million years after the solar system's formation, when a resonance crossing between Jupiter and Saturn destabilized the orbits of Uranus and Neptune, sending them careening outward through a massive disk of icy planetesimals. The consequences were cataclysmic. Neptune, plowing through the outer disk, scattered trillions of icy bodies in every direction. Some were flung into interstellar space. Some were sent inward, bombarding the inner solar system in an event called the Late Heavy Bombardment, a spike of asteroid and comet impacts roughly 3.9 billion years ago that scarred the surfaces of the Moon, Mercury, and Mars with the impact basins we see today. The lunar Maria, those dark, smooth plains visible with the naked eye, are ancient lava flows that filled impact basins created during this violent epoch. But the most dramatic event in the early solar system's history involves our own planet, and it happens roughly 50 to 100 million years after the Sun's ignition. The proto-Earth, already a substantial body of several tens of percent of its current mass, is struck by another planetary embryo roughly the size of Mars. This impactor has been named Theia, after the Greek Titanus, who was the mother of Selene, the moon goddess. The naming is apartment, because from this collision, the moon will be born. The impact is beyond catastrophic. Theia strikes the proto-Earth at a glancing angle and a velocity of roughly 4 kilometers per second. The collision releases energy equivalent to billions of nuclear weapons. Both bodies are effectively destroyed, their mantles vaporized, their cores merging into a single, seething mass of molten rock and metal. A vast disk of superheated debris, rock vapor, and liquid silicate is ejected into orbit around the newly merged body. Within centuries, perhaps less, this debris coalesces into the Moon. The evidence for the giant impact hypothesis is compelling. The Moon's composition is remarkably similar to Earth's mantle. suggesting it formed from the same material. The Moon is depleted in volatile elements and iron, consistent with formation from a disk of vaporized mantle material, while Thea's iron core merged with Earth's. And the angular momentum of the Earth-Moon system, the total spin, is consistent with a large oblique impact. The Moon is not captured. It is not co-formed. It is the child of a planetary-scale act of violence. The Moon's creation is not merely dramatic. It is consequential. The Moon stabilizes Earth's axial tilt, preventing chaotic variations that would cause extreme climate swings. Its gravitational pull drives the ocean tides that may have been crucial for the origin of life. And its presence in the sky, a celestial clock marking months and tides and seasons, has influenced the evolution of biological rhythms across the living world. The most violent event in Earth's history may also be the one that made Earth habitable. Destruction, once more, as the midwife of creation. By roughly 4.5 billion years ago, the solar system has largely taken its modern form. 8 planets orbit a stable, middle-aged star. The inner 4 are small and rocky. The outer 4 are large and gaseous or icy. Between Mars and Jupiter, a belt of asteroids marks the boundary where Jupiter's gravity prevented a planet from ever forming. Beyond Neptune, a vast disk of icy debris, the Kuiper Belt, contains remnants of the primordial solar nebula, including the dwarf planet Pluto. And farther still, the Oort cloud, a hypothetical shell of trillions of comets, extends halfway to the nearest star. The solar system is a machine of extraordinary precision and complexity, assembled from chaos and violence over tens of millions of years. Every detail of its architecture, the spacing of the planets, the composition of the asteroids, the tilt of Uranus, the rings of Saturn, tells a story of gravitational encounters, collisions, and migrations that shaped this particular arrangement from an infinite space of possibilities. It did not have to look like this. It could have been radically different, but this is what we got. And on the third planet, still cooling, still being bombarded, still glowing with the heat of its own formation, something unprecedented is about to stir. For 0.5 billion years ago, the Earth is not a planet. It is a nightmare. The surface is a churning ocean of molten rock, glowing orange and white under a sky choked with steam, carbon dioxide, and the debris of ongoing asteroid bombardment. There is no solid ground. There is no liquid water. The temperature exceeds 2,000 degrees Celsius in places. The Moon, newly born from the Theia impact, hangs enormous in the sky, perhaps 10 times closer than it is today. This is the Hadean Aeon, named after Hades, the Greek god of the underworld. The name is generous. Hades at least had a floor. The Hadean is traditionally imagined as uniformly hostile to life, but recent evidence complicates that picture. Zircon crystals from Western Australia, for 0.4 billion years old, contain oxygen isotope ratios that suggest liquid water was already present on the surface. If true, Earth cooled from a magma ocean to a habitable surface far faster than previously thought, perhaps within 100 to 200 million years of its formation. The window for life's origin may have opened earlier than anyone expected. By roughly 4.4 to 4.0 billion years ago, Earth has a solid crust, liquid water oceans, and a thick atmosphere of carbon dioxide and nitrogen. It is still being bombarded by leftover planetesimals and comets, but the rate is declining. The oceans are hot, perhaps 70 to 80 degrees Celsius, acidic, and devoid of free oxygen. The sky is hazy and orange. There is no ozone layer. Ultraviolet radiation from the young sun pours onto the surface unfiltered. And yet, somewhere in this hostile, alien environment, the most consequential chemical reaction in the history of the planet is about to occur. The origin of life is, to put it mildly, not well understood. We know it happened. We know it happened relatively quickly, geologically speaking, probably within the first billion years of Earth's history. But how non-living chemistry crossed the threshold and is replicating, metabolizing, evolving biology remains one of the deepest unsolved problems in all of science. It is not that we lack hypotheses. We have too many. The problem is choosing among them, because the evidence is 4 billion years old, fragmentary, and maddeningly ambiguous. The leading hypothesis for the site of life's origin is the deep-sea hydrothermal vent. At alkaline vents, warm, mineral-rich water seeps up through porous rock formations on the ocean floor, creating a labyrinth of tiny chambers with steep chemical gradients between the alkaline vent fluid and the acidic, iron-rich Hadean Ocean. These gradients provide a natural source of chemical energy. The porous rock provides compartments, natural protocells, and the steady flow of dissolved hydrogen, carbon dioxide, and minerals provides the raw materials for organic chemistry. The biochemist Nick Lane has argued persuasively that alkaline vents are the most plausible cradle of life. The chemistry of all living cells, he points out, still echoes the chemistry of these vents. Every cell on Earth generates energy by pumping protons across a membrane, exploiting a proton gradient to drive ADP synthesis. This is essentially what a hydrothermal vent does naturally. Life, Lane suggests, did not invent its core energy metabolism. It inherited it from the geochemistry of the ocean floor. Biology began as geology that learned to copy itself. An alternative hypothesis places the origin of life on the surface, in warm little ponds, evaporating and refilling under the Hadean sun. Charles Darwin himself speculated about a warm little pond in an 1871 letter, and modern experiments have shown that cycles of wetting and drying can concentrate organic molecules, promote polymerization, and even generate simple protocells, lipid vesicles encapsulating rudimentary genetic material. The debate between vents and ponds is vigorous, occasionally heated, and shows no signs of resolution. Life, characteristically, is not making it easy. Whatever the location, the key event is the emergence of self-replicating molecules. The RNA world hypothesis proposes that RNA, a molecule similar to DNA, but capable of both storing genetic information and catalyzing chemical reactions, was the original molecule of life. In this model, early RNA molecules that could copy themselves had a selective advantage, leading to Darwinian evolution at the molecular level long before cells, proteins, or DNA existed. RNA is both the chicken and the egg, solving the paradox of which came first by being both at once. The earliest undisputed evidence of life on Earth dates to about 3.5 billion years ago, stromatolites in Western Australia, layered structures formed by communities of microorganisms, primarily cyanobacteria, trapping and binding sediment. More controversial claims push the date back further. Carbon isotope signatures in 3.8 billion-year-old rocks from Greenland have been interpreted as biological in origin, and possible microfossils from 4.28 billion-year-old rocks in Quebec, if confirmed, would place life's origin astonishingly close to the planet's formation. Life, it seems, was not a late arrival. It was among the first things Earth did. For the first 2 billion years, life on Earth is exclusively prokaryotic, simple, single-celled organisms without a nucleus, without organelles, without any of the internal complexity we associate with modern cells. Bacteria and archaea, the two domains of prokaryotic life, dominate every habitat on the early Earth. The oceans, the seafloor, the surfaces of rocks, the shallow pools along coastlines. They are invisible to the naked eye, individually insignificant, but collectively they are about to reshape the entire planet. The agents of transformation are cyanobacteria, photosynthetic microbes that evolve the ability to split water molecules using sunlight, extracting hydrogen for their metabolism and releasing oxygen as a waste product. This process, oxygenic photosynthesis, is perhaps the most consequential metabolic innovation in the history of life. It is also, from the perspective of the existing biosphere, an act of biological terrorism. Because to the anaerobic organisms that dominate the early Earth, oxygen is not a gift. It is a poison. Cyanobacteria likely evolved oxygenic photosynthesis sometime between 3.0 and 2.7 billion years ago. But for hundreds of millions of years, the oxygen they produced did not accumulate in the atmosphere. Why? Because the early Earth was full of chemical sinks for oxygen. Dissolved iron in the oceans reacted with oxygen to form iron oxides, which precipitated out as banded iron formations, the vast rust-colored rock layers that are today mined as iron ore. The oxygen was being soaked up as fast as it was produced. The oceans essentially were rusting. Eventually, the sinks were exhausted. The dissolved iron was consumed. The reduced minerals on land were oxidized. And around 2.4 billion years ago, oxygen began to accumulate in the atmosphere in significant quantities. This event is called the Great Oxidation Event, or the GOE, and it fundamentally transformed the planet. Atmospheric oxygen rose from essentially zero to perhaps a few percent of modern levels. It was not a gradual change. In geological terms, it was abrupt. And for the anaerobic organisms that had ruled Earth for 2 billion years, it was apocalyptic. The Great Oxidation Event was the first mass extinction caused by life itself. Oxygen, a highly reactive molecule, is toxic to organisms whose biochemistry evolved in its absence. Anaerobic microbes that could not tolerate oxygen were driven to extinction or retreated to oxygen-free environments, deep sediments, hot springs, the guts of animals. The survivors adapted, evolving enzymes to neutralize oxygen's destructive effects. Some went further, evolving aerobic respiration, a metabolic pathway that uses oxygen to extract far more energy from food than anaerobic processes can. Poison became fuel. The GOE also triggered a climate catastrophe. Methane, a powerful greenhouse gas that had been keeping the early Earth warm under a fainter young sun, reacted with the newly abundant oxygen and was destroyed. Without the methane greenhouse, temperatures plummeted. The planet froze. Ice sheets spread from the poles to the tropics, and the oceans may have frozen over entirely. This is the Huronian glaciation, roughly 2.4 to 2.1 billion years ago, the first of the Great Snowball Earth episodes. Life's waste product had nearly sterilized the planet that created it. Earth eventually escaped the snowball through volcanic outgassing. Volcanoes continued to pump carbon dioxide into the atmosphere, even as the surface was frozen. With no liquid water to dissolve the CO2 through weathering, the greenhouse gas accumulated until temperatures rose enough to melt the ice. The thaw, when it came, was dramatic and rapid. The planet swung from ice house to hot house in perhaps only a few thousand years. Earth, it turns out, does not do moderation. It oscillates between extremes, and life hangs on through sheer biochemical stubbornness. Somewhere between 2.0 and 1.5 billion years ago, a pivotal event occurs that will eventually make complex life possible. A prokaryotic cell engulfs another prokaryotic cell, but instead of digesting it, the two form a symbiotic partnership. The engulfed cell becomes a mitochondrion, an internal organelle that uses oxygen to produce ADP with extraordinary efficiency. This is endosymbiosis, and it gives rise to the eukaryotic cell, a cell with a nucleus, internal membranes, and the ability to generate far more energy than any prokaryote. Every animal, plant, fungus, and protist alive today is a eukaryote. The theory of endosymbiosis was championed by Lynn Margulis, who proposed it in 1967 and spent decades defending it against skepticism that occasionally bordered on hostility. The evidence is now overwhelming. Mitochondria have their own DNA, their own ribosomes, and they replicate independently within the cell, dividing by binary fission, just like free-living bacteria. They are, in a very real sense, captive organisms, enslaved billions of years ago, and now so thoroughly integrated into their host cells that neither can survive without the other. Every breath you take is processed by the descendants of an ancient bacterium. A second endosymbiotic event occurring perhaps 1.5 billion years ago, produced the chloroplast, a eukaryotic cell engulfed a photosynthetic cyanobacterium, and the partnership gave rise to the plant lineage. From this single event, all photosynthetic eukaryotes, algae, land plants, seaweeds, descend. 2 acts of cellular engulfment, 2 ancient mergers between unrelated organisms, gave rise to the 2 most consequential innovations in the history of complex life: efficient energy production and photosynthesis. Life's greatest leaps forward were not competitive. They were collaborative. Between about 800 and 635 million years ago, Earth is hit by another series of snowball Earth glaciations, the Sturtian and Marinoan events, even more severe than the Huronian. Ice sheets extend to the equator. The oceans may freeze to a depth of a kilometer or more. Temperatures plunge to -50 degrees Celsius. And yet life survives, sheltered in pockets of open water near volcanic hot spots, in the deep ocean beneath the ice, in cracks and crevices where geothermal energy sustains microbial communities. Life, having invented the oxygen that caused the crisis, proves impossibly difficult to kill. When the ice retreats for the final time, around 635 million years ago, Earth's oceans are flush with nutrients washed from the newly exposed continents. Oxygen levels are rising again, approaching modern levels. And in the shallow seas of the late Proterozoic, something new appears. Large, soft-bodied organisms, unlike anything seen before. Frond-like shapes, disc-like forms pressed into the seafloor mud. Quilted structures of uncertain affinity. This is the Ediacaran biota, Earth's first experiment with large, multicellular life. They are strange, they are beautiful, and most of them are about to disappear. The Ediacaran organisms are enigmatic. Many of them cannot be classified into any modern animal phylum. Dickinsonia, a flat, ribbed organism that could reach over a meter in length, appears to have absorbed nutrients directly through its body surface. Charnia, a frond-like form found in deep water deposits, had no obvious mouth, gut, or means of locomotion. Some paleontologists believe the Ediacarans represent a failed experiment in multicellular life, an independent evolutionary lineage that went extinct before the Cambrian. Others see them as distant ancestors of modern animals. The fossils, as usual, keep their secrets. For 3 billion years, life on Earth was small. Microscopically, boringly, relentlessly small. Single cells, drifting and dividing, building modest stromatolite reefs in shallow seas, cycling nutrients in the deep ocean, but never in all those eons producing anything you could see without a microscope. Then, approximately 538 million years ago, in a geological heartbeat lasting perhaps 20 to 25 million years, everything changes. Animals appear, not gradually, not tentatively. They erupt into the fossil record in an avalanche of form, complexity, and innovation that paleontologists call the Cambrian explosion. The word explosion is not hyperbole. Before the Cambrian, the fossil record contains bacteria, algae, the enigmatic Ediacaran organisms, and trace fossils suggesting simple burrowing worms. After the Cambrian, it contains representatives of nearly every major animal phylum that exists today: arthropods, mollusks, chordates, echinoderms, annelids, brachiopods, and many others. In 20 million years, roughly half of 1% of Earth's history, the basic body plans of the entire animal kingdom were established. Nothing like it has happened before or since. Is biology's Big Bang. Why did it happen? This is one of the great questions in evolutionary biology, and the honest answer is, we are not entirely sure. But several factors converge in the late Precambrian and early Cambrian that together may explain the explosion. Rising oxygen levels, particularly after the last snowball Earth, provided the metabolic energy needed for large, active animals. The evolution of the Hox gene toolkit, a set of master regulatory genes that control body plan development, gave evolution new raw material to work with. And the invention of predation created a Darwinian arms race that drove innovation at breakneck speed. Predation deserves special emphasis. Before the Cambrian, there is little evidence of animals eating other animals. The Ediacaran world appears to have been one of passive filter feeders and absorbers, a Garden of Eden without predators. But in the early Cambrian, that changes. Animals evolve hard shells, sharp appendages, and crushing mouthparts. The first predators appear, and their prey respond by evolving defenses: armor, spines, burrowing behavior, speed. Each adaptation in one lineage drives counter-adaptations in others, creating an escalating feedback loop of evolutionary innovation. Peace is over. The arms race has begun. Perhaps the single most consequential innovation of the Cambrian is the eye. The first eyes appear in the early Cambrian, probably in trilobites and anomalocaridids, and they change everything. Before eyes, the ocean was a world of touch, chemical sensing, and vibration. After eyes, it became a world of sight. Predators could spot prey from a distance. Prey could see predators approaching, and natural selection suddenly had a powerful new axis of competition. Andrew Parker, in his light switch hypothesis, has argued that the evolution of vision was the primary trigger for the entire Cambrian explosion. Trilobite eyes are marvels of engineering. These arthropods, among the most successful animals in Earth's history, evolved compound eyes made of calcite crystals, the only known organism to use a mineral lens. Some trilobite species had eyes with over 15,000 individual lenses, providing nearly 360-degree vision. Others evolved schizochral eyes with individually focused lenses, essentially bifocal spectacles, 500 million years before Benjamin Franklin. Trilobites survived for 300 million years through multiple mass extinctions before finally disappearing at the end of the Permian. They earned their longevity. Our best window into the Cambrian explosion comes from a handful of extraordinary fossil sites where soft-bodied organisms were preserved in exquisite detail. The most famous is the Burgess Shale, a formation in the Canadian Rockies of British Columbia, discovered by Charles Doolittle Walcott in 1909. The Burgess Shale contains fossils of soft tissues, internal organs, even gut contents, preserved in fine-grained mudstone. It is a Cambrian Pompeii, a snapshot of an entire marine ecosystem buried and preserved by underwater mudslides over 500 million years ago. The creatures of the Burgess Shale are, to put it gently, bizarre. Anomalocaris, the abnormal shrimp, was the apex predator of its era, up to a meter long, with circular crushing mouthparts and a pair of grasping appendages at the front of its head. It had large compound eyes, possibly the sharpest in the Cambrian Ocean. For its time, Anomalocaris was the equivalent of a great white shark, except it lived 500 million years ago and looked like something designed by a committee of surrealist artists. Then there is Hallucigenia, named quite literally because its discoverer, Simon Conway Morris, thought he was hallucinating. Originally reconstructed upside, down, and backwards, with its leg where its spine should be and its head where its tail should be, Hallucigenia is a worm-like animal about 3 centimeters long, walking on 7 pairs of thin legs, with 7 pairs of rigid spines on its back. It took decades of additional fossil discoveries, including specimens from China, to work out which end was which. It is now thought to be an early relative of modern velvet worms. Opabinia may be the strangest of them all. 5 eyes, a backwards-facing mouth, a long, flexible proboscis extending forward from its head like a vacuum cleaner hose, tipped with a grasping claw. When paleontologist Harry Whittington first presented his reconstruction of Opabinia at a scientific conference in 1972, the audience burst into laughter. Not because it was wrong, because it was so extraordinarily weird that it seemed impossible. And yet the fossils are clear. Opabinia was real. Evolution, given half a chance, will try anything. Not all Cambrian organisms are so exotic. Among the fauna of the Burgess Shale is a small, unassuming creature called Pikaia. about 5 centimeters long, laterally flattened, with a notochord running along its back. Pikaia is one of the earliest known chordates. Chordates are our phylum, the lineage that includes fish, amphibians, reptiles, birds, and mammals. Pikaia, or something very like it, is our ancestor. The most important animal in the Burgess Shale is also the least visually impressive. Evolution favors the adequate, not the spectacular. Stephen Jay Gould, the Harvard paleontologist, immortalized the Burgess Shale in his 1989 book, Wonderful Life. Gould argued that the Cambrian explosion produced far more basic body plans than survive today, and that extinction, not superiority, determined which lineages persisted. If you replayed the tape of life, he famously suggested, you would get a completely different result. Our existence is not inevitable. It is contingent, accidental, a product of luck as much as adaptation. Many biologists disagreed with Gould's conclusions. None could match his prose. More recent discoveries have expanded our picture of the Cambrian far beyond the Burgess Shale. The Chengjiang biota in Yunnan province, China, is slightly older and equally well preserved. The Sirius Posset fauna in Greenland extends the record further, and new sites continue to be discovered, each one adding detail to our understanding of the Cambrian world. The picture that emerges is of an ocean teeming with complex, diverse, and often terrifying life, a world almost as rich in form as our own, but populated by creatures so alien that classifying them stretches taxonomy to its limits. The Cambrian period does not end with a bang, but it does transition into a world that, while still dominated by marine invertebrates, begins to look slightly more familiar. Trilobites diversify into thousands of species. Brachiopods carpet the seafloor. Nautiloids, ancestors of the modern nautilus, become the first large swimming predators. And the chordates, our own lineage, remains small and inconspicuous, quietly diversifying in the shadows of the arthropod empire. They are biding their time. Their moment, improbably, impossibly, is still hundreds of millions of years away. But before we leave the Cambrian, let us sit with its central mystery one more time. In 20 million years, evolution produced more fundamental innovation in animal body plans than it has in the 500 million years since. Why? We have theories. We have data. We have computer models and molecular clocks and comparative genomics. But the truth is, the Cambrian explosion remains one of the most profound and least fully explained events in the history of life. Even Darwin found it troubling. To the question why we do not find rich fossiliferous deposits belonging to these assumed earliest periods, he wrote, I can give no satisfactory answer. Neither entirely can we. The Cambrian explosion filled the oceans with life, but the land remained empty. For hundreds of millions of years after the Cambrian, the continents were barren rock and sand, scoured by wind and ultraviolet radiation, uninhabited by anything more complex than a bacterial crust. The story of the Paleozoic era, from roughly 485 to 252 million years ago, is the story of life's conquest of that emptiness. The invasion of the land by plants, arthropods, and eventually vertebrates, building ecosystems of staggering complexity on ground that had never known a footprint. The Ordovician period, from 485 to 443 million years ago, is the age of marine empire. The oceans are ruled by invertebrates on a scale the modern world can scarcely match. Trilobites scuttle across the seafloor in their thousands of species. Brachiopods encrust every available surface. Bryozoans build reef-like structures, and the great cephalopods, the nautiloids, cruise through the water column as apex predators, some growing to lengths exceeding 10 meters. The straight-shelled nautiloid Camarasaurus may have been the largest animal on Earth at the time, a tentacle predator the length of a bus. The Ordovician ends badly. Around 443 million years ago, a mass extinction kills roughly 85% of all marine species. The cause is almost certainly glaciation. The southern supercontinent, Gondwana, drifts over the South Pole, triggering the growth of massive ice sheets. Sea levels drop by hundreds of meters, draining the shallow marine habitats where most life resides. Cold, oxygen-poor water floods the remaining ocean basins. The late Ordovician extinction is the second largest in Earth's history, and it arrives with chilling speed. Millions of years of evolutionary diversity erased in a few 100,000 years. Life recovers. It always recovers. The Silurian period, from 443 to 419 million years ago, brings the first tentative colonization of a land. Small plants, not much more than green crusts and low-growing shoots, establish themselves along coastlines and riverbanks. They have no true roots, no leaves, no seeds. But they have a waxy cuticle to prevent drying out and simple vascular tissue to transport water. They are modest, unimpressive, and revolutionary. For the first time in 4 billion years, photosynthesis is happening on dry ground. Close behind the plants come the arthropods. Millipedes, scorpions, and eventually insects follow the plants onto land, drawn by the new food source and the absence of competition. The first land animals are small, often no more than a centimeter or two in length, but they establish the template for terrestrial ecosystems. Plants at the base, herbivores consuming them, predators consuming the herbivores. This ecological structure, first assembled in the Silurian, persists in recognizable form to the present day. The Silurian also witnesses a pivotal innovation in the oceans, the evolution of jaws. The first jawed vertebrates, the gnathostomes, appear in the Silurian and will ultimately give rise to every vertebrate with jaws alive today. Sharks, bony fish, amphibians, reptiles, birds, mammals. Before jaws, vertebrates were passive filter feeders, sucking mud and water through jawless mouths. Jaws transformed them into active predators, capable of biting, tearing, and manipulating food. The jaw is, pound for pound, one of the most consequential innovations in vertebrate history. The Devonian period from 419 to 359 million years ago is called the Age of Fishes, and it earns the title. The oceans swarm with jawed fish of extraordinary diversity. Placoderms, armored fish with bony plates covering their heads, include Dunkleosteus, a predator up to 8 meters long with shearing jaw plates that could bite with a force rivaling a modern alligator. Sharks appear and begin their long, spectacularly successful evolutionary career. And the bony fish, ancestors of most modern fish, diversify into thousands of species. But the Devonian's most important event happens at the water's edge. A group of lobe-finned fish with fleshy, muscular fins supported by internal bones, begin to spend time in the shallows. Their fins, sturdy enough to prop their bodies on the bottom, gradually evolve into limbs. Their swim bladders, already used for buoyancy, begin to function as primitive lungs. And over millions of years, these transitional creatures, neither fully fish nor fully amphibian, drag themselves onto land. The vertebrate conquest of the continents has begun. The poster child for this transition is Tiktaalik rosei, discovered in 2004 by Neil Shubin and colleagues in the Canadian Arctic. Tiktaalik lived about 375 million years ago and is exquisitely intermediate between fish and land vertebrates. It has gills and scales like a fish, but also a flat head, a neck that can turn independently of its body, and robust, jointed fins that function like primitive legs. Shubin titled his popular book about the discovery, Your Inner Fish, because Tiktaalik's anatomy is a direct precursor to our own limb structure. Your wrist bones are its fin bones. The Devonian also sees the explosion of land plants into their first great forests. By the late Devonian, trees have evolved. Archaeopteris, a genus that could reach 30 meters in height, forms extensive forests across the tropical and temperate continents. These forests transform the planet. Their roots break up rock, accelerating weathering and soil formation. Their leaves absorb CO2, drawing down atmospheric carbon dioxide and cooling the climate. The spread of forests may have triggered the late Devonian extinction events through over-enthusiastic carbon sequestration, dropping CO2 and temperatures to lethal levels. Trees, both the builders and the destroyers of worlds. The Carboniferous period, from 359 to 299 million years ago, is an era of biological excess. Atmospheric oxygen levels soared to roughly 35%, compared to today's 21%, driven by the burial of vast quantities of dead plant matter in swampy forests that cover much of the tropical landmass. This oxygen-rich atmosphere permits arthropods to grow to sizes that would be physically impossible today. Insects breathe through spiracles, passive channels in their exoskeletons, and the maximum body size is limited by oxygen diffusion. More oxygen means bigger bugs. And when we say bigger bugs, we mean considerably bigger. Meganeura, a dragonfly relative, had a wingspan of roughly 70 centimeters, nearly 2.5 feet. Arthropleura, a giant millipede, reached lengths of 2.3 meters and weighed an estimated 50 kilograms, making it the largest land arthropod known to have ever existed. Imagine encountering a millipede the length of a small car, scuttling through the fern undergrowth of a Carboniferous swamp. The Carboniferous is proof that the past is a foreign country, and occasionally a terrifying one. The Carboniferous swamps are significant for another reason. They're the source of nearly all the world's coal deposits. The vast forests of giant lycopsids, tree ferns, and early conifers that carpeted the Carboniferous tropics grew, died, and fell into waterlogged and noxic swamps where their wood could not fully decompose. The reason is extraordinary. The fungi that evolved to break down lignin, the structural polymer in wood, had not yet appeared. For tens of millions of years, deadwood piled up because nothing on Earth could eat it. The result was a 60 million year accumulation of fossilized plant matter that humans would one day dig up and burn to power an industrial revolution. During the Carboniferous, the first reptiles evolved from amphibian ancestors. The key innovation is the amniotic egg, an egg with a waterproof shell and internal membranes that allow the embryo to develop on dry land, free from dependence on water for reproduction. This seems like a modest achievement, but it is transformative. Amphibians must return to water to breed. Reptiles do not. The amniotic egg allows vertebrates to colonize the continental interiors for the first time, unlocking vast new habitats that were previously inaccessible. A small change in reproductive biology reshapes the geography of life. The Permian period, from 299 to 252 million years ago, sees the continents assemble into the supercontinent Pangaea, a single, vast landmass stretching from pole to pole. Pangaea's interior is dry, seasonal, and extreme, with massive deserts in the center and monsoon climates along the coasts. Life adapts. Reptiles diversify into numerous lineages, including the synapsids, a group that, despite their reptilian appearance, are actually the ancestors of mammals. Dimetrodon, the famous sail-back predator of countless children's dinosaur books, is not a dinosaur at all. It is a synapsid, and it is more closely related to you than to any dinosaur. And then, 252 million years ago, the world ends. Not metaphorically, not partially, nearly completely. The Permian-Triassic extinction event, also called the Great Dying, is the worst catastrophe in the history of complex life on Earth. 96% of all marine species disappear. 70% of terrestrial vertebrate species vanish. Even insects, that most resilient of groups, suffer massive losses. The biosphere is pushed to within a breath of total annihilation. Nothing before or since has come as close to erasing complex life from the planet. The cause is volcanic. The Siberian Traps, one of the largest volcanic events in Earth's history, erupt across what is now northern Russia, pouring out roughly 3 million cubic kilometers of lava over a period of perhaps 1 million years. But the lava is not the primary killer. The magma intrudes into vast deposits of coal and limestone in the Siberian crust, cooking them and releasing staggering quantities of carbon dioxide, methane, and sulfur dioxide into the atmosphere. The result is rapid, extreme global warming, ocean acidification, and the depletion of dissolved oxygen in the seas. Temperatures rise by 10 to 15 degrees Celsius globally. The oceans become a hot, acidic, oxygen-depleted death trap. Coral reefs disappear entirely and will not return for millions of years. On land, forests collapse. Soil erosion accelerates. Wildfires rage across desiccated continents. The atmosphere may have become toxic with hydrogen sulfide, the gas that smells of rotten eggs, reaching lethal concentrations in some regions. The killing lasts for perhaps 60,000 years, a geological instant, an eternity for the organisms enduring it. Recovery from the Great Dying is the slowest of any mass extinction. It takes 10 million years for marine ecosystems to return to pre-extinction levels of diversity. On land, the recovery is dominated by a single genus, Lystrosaurus, a pig-sized, tusked herbivore that somehow survived the extinction and thrived in the post-apocalyptic world, accounting for an estimated 95% of all land vertebrate individuals in some early Triassic fossil assemblages. For millions of years, the continents belonged to this one humble survivor. It is the most successful vertebrate of all time, and nobody outside paleontology has heard of it. The Permian-Triassic extinction is a warning. It demonstrates that life, however tenacious, however adaptable, can be pushed to the very edge of total destruction by rapid changes in atmospheric chemistry and global temperature. The mechanisms that killed 96% of marine species 252 million years ago, greenhouse gas emissions, ocean warming, acidification, and deoxygenation, are the same mechanisms operating in Earth's oceans today, driven now not by Siberian volcanism, but by human industry. The parallel is uncomfortable. It is meant to be. The Triassic world is a ruin. In the aftermath of the Great Dying, the continents are hot, dry, and biologically impoverished. The lush forests and diverse ecosystems of the late Permian are gone, replaced by arid scrublands dominated by the survivor genus Lystrosaurus. The oceans are nearly sterile. Coral reefs have vanished. The biosphere is a blank canvas, and evolution, ever opportunistic, is about to paint on it with the broadest strokes in its history. The Triassic period, from 252 to 201 million years ago, is the incubation chamber for the Mesozoic's dominant lineage, the Archosaurs. This group, which includes crocodilians, pterosaurs, and dinosaurs, begins the Triassic as a minor component of the reptile fauna. But they have advantages. Many archosaurs are bipedal, freeing their forelimbs for other uses. Some evolve upright postures, placing their legs directly beneath their bodies rather than sprawling to the sides, enabling more efficient locomotion. These innovations, modest at first, will prove decisive. The earliest known dinosaurs appear in the fossil record around 231 million years ago in what is now Argentina and Brazil. They are small, mostly bipedal, and unimpressive. Eoraptor, roughly the size of a dog, is one of the earliest. Heterosaurus, somewhat larger, is a predator of modest ambition. These animals are not the rulers of their ecosystems. They are minor players, outnumbered and outweighed by larger archosaur relatives and surviving therapsids. Dinosaurs do not seize power. They inherit it after another mass extinction clears the way. That extinction arrives at the end of the Triassic, roughly 201 million years ago, driven by the eruption of the Central Atlantic Magmatic Province, CAMP, as Pangaea begins to rift apart. The end Triassic extinction kills many of the archosaur groups that have been competing with dinosaurs, as well as numerous marine and vertebrate groups. In the aftermath, dinosaurs find themselves with few competitors and vast, empty ecological niches. They diversify explosively. By the early Jurassic, they're the dominant terrestrial vertebrates on every continent. The Mesozoic is theirs. The Jurassic period, from 201 to 145 million years ago, is the Age of Giants. The sauropods, long-necked herbivorous dinosaurs, evolved to sizes that strain credulity. Brachiosaurus stands 13 meters tall, its head reaching the canopy of conifer forests. Diplodocus stretches 25 meters from nose to tail tip, its whip-like tail cracking supersonically as a defensive weapon. And Argentinosaurus, one of the largest land animals ever to have lived, may have weighed close to 70 tons, 10 times the mass of the largest modern elephant. How could an animal grow so large? Several factors conspire. Sauropods have a bird-like respiratory system with air sacs that lightens their skeletons and provides efficient oxygen exchange. They do not chew their food, eliminating the need for a heavy jaw and allowing the head to remain small and the neck to extend to extraordinary lengths. And their metabolic rate, probably intermediate between modern reptiles and mammals, allows them to sustain large body sizes without the enormous caloric demands of a fully endothermic metabolism. They are biological engineering at its most audacious. The Jurassic also sees the appearance of the first birds. Archaeopteryx, discovered in 1861 in the limestone quarries of Solnhofen, Germany, is one of the most important fossils ever found. It has feathers and a wishbone like a bird, but teeth, claws on its wings, and a long bony tail like a theropod dinosaur. It is transitional, and it was discovered just 2 years after Darwin published On the Origin of Species. The timing was almost too perfect. Even Thomas Huxley, Darwin's most fierce defender, was delighted. We now know that Archaeopteryx is not an anomaly. Bird or dinosaurs. Specifically, they are a surviving lineage of theropod dinosaurs, the same group that includes Velociraptor and Tyrannosaurus rex. Feathers, once thought to be uniquely avian, have been found on dozens of non-avian theropod species, some of them large, fearsome predators. The discovery of feathered dinosaurs in the Liaoning province of China, beginning in the late 1990s, revolutionized our understanding of dinosaur biology. Your pet parrot is a living dinosaur. The extinction was not total. It was selective. The Cretaceous period, from 145 to 66 million years ago, is the Mesozoic's grand finale, and it is spectacular. Dinosaurs reached their peak diversity. Tyrannosaurus rex, perhaps the most famous animal in history, stalks the late Cretaceous landscapes of western North America. 12 meters long, weighing up to 9 tons, with a bite force estimated at 12,800 pounds, the strongest of any terrestrial animal ever measured. It is the apex predator perfected, the ultimate expression of 186 million years of dinosaur evolution. But Rex is only one player in a cast of thousands. Triceratops, with its 3 horns and massive bony frill, is one of the last and most successful ceratopsians. Hadrosaurs, the duck-billed dinosaurs, travel in vast herds across the Cretaceous plains, their elaborate crests possibly serving as resonating chambers for long-distance communication. Ankylosaurs, armored like living tanks, carry bony clubs on their tails capable of shattering the leg bones of attacking tyrannosaurs. The late Cretaceous is an arms race frozen in bone. The oceans of the Mesozoic are equally dramatic. Ichthyosaurs, dolphin-shaped reptiles with enormous eyes and streamlined bodies, dominate the early and middle Mesozoic seas. Plesiosaurs, with their long necks and paddle-like limbs, persist throughout the era. And in the late Cretaceous, the mosasaurs appear. Enormous, predatory marine lizards, some exceeding 15 meters in length, that become the ocean's undisputed apex predators. Meanwhile, above the waves, pterosaurs with wingspans exceeding 10 meters soar on thermals. Quetzalcoatlus, with a wingspan of 10 to 11 meters, is the largest flying animal ever known. The Cretaceous also witnesses one of the most consequential biological revolutions in the history of terrestrial ecosystems, the rise of flowering plants. Angiosperms appear in the fossil record around 130 million years ago, and by the late Cretaceous, they have diversified explosively, outcompeting the conifers, ferns, and cycads that had dominated Mesozoic vegetation. Their secret weapon is the flower itself, a structure designed to attract pollinators, enabling more efficient, more targeted reproduction. Flowers co-evolve with insects, and together they reshape every terrestrial ecosystem on the planet. By 66 million years ago, the dinosaur empire appears unshakable. They have dominated every terrestrial ecosystem for 186 million years, surviving multiple climate shifts, volcanic events, and continental rearrangements. They occupy every continent, from polar forests to tropical lowlands. They range from the size of a pigeon to the size of a building. No group of land animals has ever maintained such total dominance for so long. They seem invincible. And then, on a perfectly ordinary late Cretaceous afternoon, a rock the size of a city falls out of the sky. The Chicxulub impactor is approximately 10 to 15 kilometers in diameter. It enters Earth's atmosphere at roughly 20 kilometers per second, a speed so great that the air in front of it does not have time to move aside. It superheats into a glowing plasma. The asteroid strikes the shallow seas off what is now the Yucatan Peninsula of Mexico, punching through the water and the crust in less than a second. The impact releases energy equivalent to roughly 10 billion Hiroshima bombs. The explosion excavates a crater 180 kilometers wide and 20 kilometers deep. The immediate effects are apocalyptic. A fireball, hotter than the surface of the sun, expands outward from the impact site, incinerating everything within 1,000 kilometers. Tsunamis hundreds of meters high race across the Gulf of Mexico, scouring coastlines as far as the modern Gulf states. Billions of tons of vaporized rock are launched into the upper atmosphere in orbit, where they're entered globally, heating the atmosphere to oven-like temperatures for several hours. Forests ignite worldwide. Animals caught in the open are cooked alive. But the worst is yet to come. The impact site happens to be rich in sulfate-bearing rocks. Billions of tons of sulfur aerosols are injected into the stratosphere, where they block sunlight for years. Temperatures drop by 10 to 15 degrees Celsius. Photosynthesis ceases. The base of the food chain collapses. In the oceans, the plankton die. The creatures that feed on plankton die. The creatures that feed on those creatures die. It is a cascading extinction, driven from the bottom up, powered not by the impact itself, but by the years of darkness and cold that follow. Nuclear winter, 66 million years early. The evidence for the impact is overwhelming. In 1980, Luis and Walter Alvarez, a father and son team of physicists and geologists, discovered a thin layer of clay at the Cretaceous-Paleogene boundary enriched in iridium, an element rare on Earth but common in asteroids. The iridium layer is found worldwide at precisely the same stratigraphic level, a global calling card of extraterrestrial violence. The crater itself was identified in the early 1990s, buried beneath younger sediments in the Yucatan. The case is closed. The dinosaurs were killed by a rock from space. 75% of all species on Earth perish in the Cretaceous-Paleogene extinction. Every non-avian dinosaur, every pterosaur, every mosasaur, plesiosaur, and ammonite. Most of the marine plankton, the large-bodied, the slow-reproducing, the ecologically specialized, gone. What survives tends to be small, fast-breeding, ecologically flexible, or capable of entering a dormant state. Crocodilians survive. Turtles survive. Small mammals, sheltering underground, survive. And the birds, those feathered theropod dinosaurs, endure the catastrophe and fly out the other side. The age of reptilian supremacy is over. But the age of the dinosaurs, in one small, feathered sense, continues to this day. The dust settles. The sky is clear. Sunlight returns to a planet that has not seen it in years. And on this battered, ash-covered, biologically devastated Earth, the survivors blink, emerge from their burrows and hiding places, and survey a world emptied of its dominant inhabitants. The dinosaurs are gone. After 186 million years of unbroken reign, every non-avian species has been erased in a geological instant. The ecological niches they occupied, from the canopy to the ocean floor, are vacant. Nature, as always, abhors a vacuum, and something warm-blooded is about to fill it. Mammals had existed alongside dinosaurs for over 150 million years, but they have been confined to the margins, small, mostly nocturnal, mostly insectivorous, skulking in the underbrush while the dinosaurs commanded the stage. The largest Mesozoic mammals were roughly the size of a badger. Most were smaller than a mouse. They were, by any measure, bit players in the Mesozoic drama. But they had two critical advantages: warm-bloodedness, which allowed them to function efficiently at night and in cold conditions, and live birth combined with lactation, which enabled intensive parental care. Within 10 million years of the extinction, mammals undergo one of the most explosive adaptive radiations in evolutionary history. They diversify into body plans that would have been unimaginable during the Mesozoic. Herbivores the size of rhinos, predators the size of bears, whales descending from small, wolf-like ancestors and returning to the sea, bats taking to the air, primates ascending into the canopy. Every ecological role vacated by the dinosaurs is filled by a mammal. The Cenozoic era, from 66 million years ago to the present, is the age of mammals. The early Cenozoic is a hothouse world. Temperatures in the Paleocene and Eocene epochs are significantly warmer than today, with tropical forests extending to latitudes as high as 60 degrees north and south. There is no permanent ice at either pole. Palm trees grow in Alaska. Crocodilians bask on the shores of the Arctic Ocean. The planet is warm, wet, and covered in dense vegetation from equator to pole. It is paradise if you happen to be a mammal with no particular fondness for snow. The Paleocene-Eocene thermal maximum, or PTM, roughly 56 million years ago, is the most extreme warming event of the Cenozoic. A massive release of carbon, possibly from volcanic activity, methane hydrate destabilization, or both, drives global temperatures up by 5 to 8 degrees Celsius in less than 20,000 years. Ocean acidification kills deep-sea organisms. Tropical conditions extend to the poles. The PTM lasts about 200,000 years before the carbon is slowly reabsorbed. It is a natural experiment in rapid carbon release, and the parallels to modern climate change are studied intensively by climate scientists today. Among the most remarkable evolutionary stories of the Cenozoic is the return of mammals to the sea. Whales descend from a group of small, terrestrial, even-toed ungulates related to modern hippos. The transition from land to sea is documented in an extraordinary series of transitional fossils from Pakistan and India. Pakicetus, roughly 50 million years old, is a wolf-sized terrestrial predator with the ear bones of a whale. Ambulocetus, the walking whale, is a semi-aquatic ambush predator. Basilosaurus, despite its reptilian name, is a fully marine whale 15 meters long. The entire transition from land to ocean takes roughly 10 million years. Horse evolution is another textbook case, though the textbook version is misleadingly simple. The ancestral horse, Eohippus or Hyracotherium, was a small, dog-sized animal with 4 toes on its front feet, living in the forests of the early Eocene. Over 55 million years, the horse lineage underwent dramatic changes: increasing body size, reduction of toes from 4 to 1, elongation of legs for running, and changes in dentition from leaf browsing to grass grazing. But this was not a linear march of progress. The horse family tree is a bush with many branches, many dead ends, and many species alive simultaneously. The reason horses evolved longer legs and specialized teeth is that the world was changing beneath their feet. Beginning in the late Eocene and accelerating through the Oligocene and Miocene, roughly 35 to 5 million years ago, global temperatures declined and grasslands spread across the interiors of continents. Forest retreat. Opened, Grassy plains expand across North America, South America, Africa, and Asia. This ecological revolution transforms terrestrial ecosystems, favoring animals adapted for running on open ground, grazing on tough, silica-rich grasses, and scanning the horizon for predators. The cause of this long-term cooling trend is partly tectonic. The collision of the Indian subcontinent with Asia, beginning roughly 50 million years ago, pushes up the Himalayas, the Tibetan Plateau, and the Karakoram Range. These enormous mountain ranges alter atmospheric circulation patterns, increase weathering of silicate rocks, which consume CO2, and contribute to the long-term drawdown of atmospheric carbon dioxide. The closing of the Tethys Sea and the opening of the Drake Passage further alter ocean circulation, isolating Antarctica and allowing the formation of the Antarctic Circumpolar Current. Around 34 million years ago, at the Eocene-Oligocene boundary, Earth's climate crosses a critical threshold. Antarctica, now thermally isolated by the circumpolar current, develops a permanent ice sheet for the first time since the Permian. Sea levels drop. Global temperatures decline further. The transition from a greenhouse world to an icehouse world is underway, and it will continue with fluctuations for the next 34 million years, culminating in the Pleistocene ice ages that will shape the final chapter of human evolution. The Miocene epoch from 23 to 5.3 million years ago is the golden age of mammalian megafauna. On every continent, large mammals reach their peak diversity. Africa is home to dozens of species of proboscideans, ancestors of modern elephants. North America hosts herds of horses, camels, and rhinoceroses. South America, isolated as an island continent, develops its own unique megafauna. Giant ground sloths, armadillo-like glyptodonts, and the terrifying forest wrasses, terror birds, flightless predators standing 3 meters tall. The Miocene world is a safari park of extraordinary richness. It is in the forests of Miocene Africa that our own story takes its most consequential turn. Primates have been evolving since the early Cenozoic. Lemur-like primates appear in the Paleocene. Monkeys diverged from the primate lineage around 40 million years ago. The great apes, the hominids, emerge in Africa during the Miocene, between about 20 and 15 million years ago. Proconsul, a tailless, fruit-eating ape from East Africa, is among the earliest well-known members of this group. It walks on all fours, lives in trees, and has no idea what its descendants will become. During the late Miocene, roughly 10 to 7 million years ago, the great ape lineage branches repeatedly. The ancestors of orangutans diverge first, followed by gorillas, and finally, somewhere between 7 and 6 million years ago, the lineage leading to chimpanzees and bonobos separates from the lineage leading to humans. This last divergence, this final fork in the road, occurs in Africa, probably in the context of drying forests and expanding grasslands that create new environmental pressures and new opportunities. Two lineages walk away from each other. One stays in the forest, the other steps out. We do not know what the last common ancestor of humans and chimpanzees looked like. We do not have its fossil, or if we do, we have not recognized it. But we know it lived in Africa. We know it was a great ape, probably arboreal, probably social, probably no more remarkable than any other Miocene primate. And we know that from its descendants, from one lineage that happened to stand upright, happened to pick up stones, happened to develop a brain disproportionate to its body, will come language, art, cities, war, science, and the capacity to look back across 7 million years and wonder how it all began. The Cenozoic is not yet over. We're living in it. The age of mammals continues, though age of mammals increasingly feels like a euphemism for age of one particular mammal that has gotten wildly out of hand. But that is a story for the next chapter. For now, let us note that in the grand sweep of cosmic history, the rise of the mammals is a recent event. If the 13.8 billion year history of the universe were compressed into a single calendar year, the entire Cenozoic era, from the asteroid impact to the present, would occupy the last 10 minutes of December 31st. We are latecomers. Extraordinarily latecomers. 7 million years ago, in the forests of what is now Chad, in Central Africa, an ape dies. Its skull fossilizes. 6,997,000 years later, a team led by Michel Brunet discovers it and names it Sahelanthropus cadensis, nicknamed Tumai, a word meaning hope of life in the local Goran language. Tumai's skull has a small brain, about the size of a chimpanzee's, a flat face, and a foramen magnum, the hole where the spinal cord meets the skull, positioned underneath rather than at the back. This positioning suggests upright posture. Tumai may have walked on 2 legs. If so, it is the oldest known hominin, the oldest member of our family. Let's be clear about terminology. A hominin is any member of the human lineage after it diverged from the lineage leading to chimpanzees and bonobos. It does not mean human. It means closer to us than to chimps. The hominin family tree is not a straight line from ape to human. It is a bush, a dense, tangled, repeatedly pruned bush with dozens of species, most of them evolutionary dead ends, many of them living simultaneously. We're the only surviving twig. That should make us humble. It usually does not. Between 7 and 4 million years ago, several hominin species leave fragmentary traces in the fossil record. Auroran tugenensis from Kenya, Ardipithecus cadaba, and Ardipithecus ramidus from Ethiopia. Ardipithecus ramidus, known affectionately as Ardi, lived about 4.4 million years ago in a forested environment and combined an upright gait with a grasping big toe, suggesting it walked on the ground but still spent significant time in the trees. Ardi is a mosaic, part bipedal ground walker, part arboreal climber. Evolution does not make clean breaks. It tinkers. 4 million years ago, the Australopithecines have arrived. Australopithecus anamensis, Australopithecus afarensis, Australopithecus africanus, a constellation of species spread across eastern and southern Africa, all bipedal, all small-brained, all fundamentally ape-like from the neck up, but increasingly human-like from the neck down. They are the first hominins for which we have substantial fossil evidence, and the most famous individual among them is a 3.2 million-year-old Australopithecus afarensis skeleton from Ethiopia, known to the world as Lucy. Lucy was discovered in 1974 by Donald Johanson and Tom Gray at Hadar, in the Afar region of Ethiopia. She was named after the Beatles' song Lucy in the Sky with Diamonds, which was playing at the expedition camp on the night of her discovery. She stood about 1.1 meters tall, weighed roughly 29 kilograms, and had a brain about 1/3 the size of a modern human's. She walked upright, as confirmed by her pelvis and knee joint. She is not our direct ancestor, but she is close. She is a cousin, a fellow traveler on the hominin branch, frozen in time by the sediments of the Awash River. The Litoli footprints, discovered in Tanzania in 1978 by Mary Leakey's team, provide even more dramatic evidence of early hominin bipedalism. Preserved in volcanic ash dated to 3.66 million years ago, the footprints show 2 or 3 individuals walking upright across a freshly deposited ash layer. The prints are remarkably human-like. A clear heel strike, a longitudinal arch, a big toe aligned with the other toes, no hand impressions. These individuals walked like us. They were not shuffling or crouching. They strode across the ash with a confident, modern gait 3.66 million years before anyone invented shoes. Around 3.3 million years ago, the first stone tools appear. Found at Lomekwi in Kenya, these crude, deliberately knapped stones predate the genus Homo entirely, suggesting that Australopithecines, or related hominin, were already modifying rocks for cutting and pounding. The Lomekwi tools are simple, cobbles struck against each other to produce sharp flakes, but they represent something profound. An animal is deliberately modifying objects in its environment to serve a purpose. This is technology, primitive, rudimentary, but unmistakable. The toolmaker has arrived. The Oldowan tradition, named after Oldoway Gorge in Tanzania, represents the next major advance in stone tool technology, beginning about 2.6 million years ago. Oldowan tools are more refined. Cores struck to produce multiple sharp flakes used for cutting meat, scraping hides, and processing plant material. They are associated with early members of the genus Homo, including Homo habilis, the handyman, a species with a brain about 50% larger than an Australopithecines. Whether Homo habilis deserves to be called Homo or is an advanced Australopithecine remains the subject of vigorous academic debate, which is academic speak for we argue about it at conferences. Homo erectus changes everything. Appearing in the fossil record around 1.9 million years ago, Homo erectus is the first hominin to look broadly human-like in body proportions. Tall, long-legged, relatively short-armed, with a body clearly built for efficient long-distance walking and running. Its brain is significantly larger than any earlier hominin, roughly 900 cubic centimeters compared to 450 for an Australopithecine. And it is the first hominin to leave Africa, spreading across Asia and into parts of Europe by at least 1.8 million years ago. Homo erectus masters fire. The evidence is debated for the earliest dates, but by roughly 400,000 years ago, and possibly much earlier, controlled use of fire is well established. Fire is transformative. It provides warmth, extending the habitable range of hominins into colder climates. It provides light, extending the useful hours of the day. It detours predators. And, most importantly, it allows cooking, which breaks down tough plant fibers and denatures proteins, effectively pre-digesting food outside the body and making far more calories available. Cooking may have fueled the expansion of the hominin brain. The Acheulean hand axe, associated primarily with Homo erectus, is arguably the most successful tool design in history. A teardrop-shaped stone, carefully napped on both faces to produce a symmetrical cutting edge. The Acheulean hand axe appears in the archaeological record around 1.76 million years ago and persists largely unchanged for over a million years. A million years. The same basic design, replicated across 3 continents, for longer than our entire species has existed. Whatever Homo erectus lacked in innovation, it made up for inconsistency. Homo erectus is not alone. The hominin family tree during the Pleistocene is crowded. In Africa, Homo heidelbergensis, a larger brain species, appears around 700,000 years ago and is thought to be the common ancestor of both modern humans and Neanderthals. In Southeast Asia, the diminutive Homo floresiensis, standing barely a meter tall, survives on the island of Flores until as recently as 50,000 years ago. In the Philippines, Homo luzonensis is described from fragmentary remains in Calao Cave. The genus Homo is a diverse, widespread, multi-species affair. We were never the only humans on the planet. And then there are the Neanderthals. Homo neanderthalensis evolves in Europe and Western Asia roughly 400,000 years ago, adapted to the cold, harsh, glacial environments of the Ice Age. They're stocky, powerfully built, with brains as large as or larger than those of modern humans. They make sophisticated stone tools, the Mousterian tradition. They bury their dead. They care for injured and elderly group members. They may have used pigments decoratively. They are, by any reasonable measure, intelligent, social, culturally complex beings. They're also about to vanish. The Denisovans, identified not from skeleton but from DNA extracted from a finger bone found in a Siberian cave in 2010, add another branch to the hominin bush. We know almost nothing about what they looked like, but we know they were widespread across Asia, that they interbred with both Neanderthals and modern humans, and that their DNA lives on today in modern Melanesian and Australian Aboriginal populations, who carry up to 5% Denisovan DNA. The ghosts of extinct human species haunt our genomes. We carry their legacy in every cell. Homo naledi, discovered in the Rising Star cave system in South Africa in 2013 by a team led by Lee Berger, complicates the picture even further. With a brain roughly one-third the size of a modern human's, Homo naledi has a mosaic of primitive and derived features that defies easy classification. Most provocatively, the bodies were found deep in a difficult-to-access cave chamber, suggesting deliberate disposal of the dead, a behavior previously attributed only to large-brained hominins. If Homo naledi was indeed burying its dead, then complex symbolic behavior may not require a large brain. Our assumptions may need revision. Anatomically modern Homo sapiens appears in the fossil record roughly 300,000 years ago, based on fossils from Jebel Irhoud in Morocco, dated in 2017. This is significantly older than the previous estimate of about 200,000 years, and suggests that our species did not evolve in a single location, but may have emerged across a geographically dispersed African population, connected by gene flow across the continent. We are not the product of a single birthplace. We are a pan-African species, forged across a continent. Early Homo sapiens has the anatomy of a modern human, but not yet the behavior. For the first 100,000 years or so, the archaeological record shows tools and behaviors that are not dramatically different from those of Neanderthals or late Homo erectus. There are hints of symbolic thought. Shell beads from Blombos Cave in South Africa dated to 75,000 years ago, ochre pigments with engraved geometric patterns. But the full flowering of modern human behavior, art, music, complex language, long-distance trade, explosive technological innovation, comes later. The hardware is in place. The software is still loading. And what about those other humans? The Neanderthals disappear from the fossil record around 40,000 years ago, shortly after modern humans arrive in Europe. Homo floresiensis vanishes around 50,000 years ago. The Denisovans fade from the record at roughly the same time. Homo erectus, the great survivor that had persisted for nearly 2 million years, may have lingered in Java until as recently as 110,000 years ago. One by one, every other human species goes extinct. The timing is suspicious. We arrive and they vanish. Coincidence is possible, but uncomfortable. Whether Homo sapiens directly caused the extinction of other human species through competition, violence, disease, or simply by outbreeding and outcompeting them for resources remains one of the most emotionally charged questions in paleoanthropology. We know we interbred with Neanderthals. Most non-African humans carry 1 to 4% Neanderthal DNA. We know we interbred with Denisovans. But interbreeding and replacement are not mutually exclusive. You can absorb a population genetically while destroying it culturally and demographically. The result looks, in the fossil record, exactly the same as extinction. By roughly 40,000 years ago, Homo sapiens is the last hominin standing. For the first time in 7 million years of hominin evolution, a single species has a monopoly on the human niche. We are alone, not because we are the best, not because we are the chosen, but because every other experiment in human cognition, every other variation on the bipedal, big brain, tool-using primate theme has been tested and has failed, or been eliminated. We are the survivors of family tragedy, and the evidence suggests we may have caused some of it ourselves. Sometime between 100,000 and 70,000 years ago, something shifts inside the sapiens' mind. The archaeological record, previously modest and largely indistinguishable from the toolkits of other hominins, begins to show signs of something genuinely new. Shell beads appear, strung into necklaces, suggesting personal adornment and social signaling. Ochre pigments are mixed and applied to bodies and objects. Bone tools become more refined. Trade networks emerge, moving obsidian and shells over distances of hundreds of kilometers. Something has changed. Scholars call it the cognitive revolution, and it is arguably the most important event in the history of life on Earth. What exactly changed? This is fiercely debated. Some researchers, like Richard Klein, argue for a sudden genetic mutation that rewired the brain for complex language, creating a biological revolution around 50,000 years ago. Others, like Sally McBrearty and Alison Brooks, argue that modern cognitive abilities emerged gradually across Africa over hundreds of thousands of years, and the apparent revolution is an artifact of a biased European archaeological record. The truth probably lies somewhere in between, as truths tend to do, stubbornly refusing to cooperate with clean narratives. Whatever the mechanism, the result is clear. Homo sapiens develops the capacity for symbolic thought, the ability to create and manipulate abstract concepts, to communicate them through language, and to build shared fictions that enable cooperation among thousands of strangers. Yuval Noah Harari, in his book *Sapiens*, argues that this capacity for fiction, the ability to believe in things that exist only in collective imagination, gods, nations, money, human rights, is the defining feature of our species. No other animal can convince 10,000 strangers to cooperate toward a common goal. Humans do it routinely. Language is the engine of this revolution. While many animals communicate, human language is unique in its recursive structure, its capacity for displacement, discussing things not present in time or space, and its ability to express hypothetical and counterfactual ideas. What if, imagine that once upon a time, these phrases represent cognitive abilities no other species possesses? Language allows the accumulation and transmission of knowledge across generations. It creates culture, and culture evolves far faster than biology. With language, humans step off the slow conveyor belt of genetic evolution and onto the rocket of cultural evolution. The most spectacular evidence of the cognitive revolution is art. The cave paintings of Chauvet in southern France, dated to roughly 36,000 years ago, are among the oldest known works of figurative art. They depict lions, horses, rhinoceroses, and mammoths with a skill and dynamism that astounded their discoverers. These are not crude scratchings. They are sophisticated compositions, using perspective, shading, and even a primitive form of animation. Animals drawn with multiple legs to suggest motion. The artists of Chauvet were masters of their craft, working by flickering torchlight in the depths of the earth. The caves at Lascaux, Altamira, and dozens of other sites across Europe and Southeast Asia, plus the recently discovered figurative art in Sulawesi, Indonesia, dated to at least 45,500 years ago, confirm that the artistic impulse is universal. These are not decorations. They are statements of consciousness. An animal that paints a bison on a cave wall is an animal that can hold an image in its mind, abstract it from reality, and project it onto a surface. It is an animal that knows it exists. It is an animal that thinks about thinking. That is new. In 4.5 billion years of life on Earth, nothing has ever done that before. Armed with language, symbolic thought, and the capacity for complex social organization, Homo sapiens begins to move. The Great Migration out of Africa starts in earnest roughly 70,000 years ago, though earlier, smaller dispersals may have occurred and failed. The route leads out of northeast Africa, across the southern end of the Red Sea, or through the Sinai Peninsula, and into the Middle East. From there, the human tide splits, one branch heading east along the southern coast of Asia, another eventually turning north into Europe and Central Asia. The speed of the coastal migration is remarkable. Following the shorelines of the Indian Ocean, human groups move through southern Arabia, India, and Southeast Asia, reaching Australia by at least 65,000 years ago. This requires the construction of watercraft because even at glacial sea level lows, Australia was never connected to Asia by a land bridge. The first Australians, ancestors of modern Aboriginal Australians, crossed at least 90 kilometers of open ocean to reach their new home. It is the earliest evidence of deliberate ocean voyaging by any species in history. Europe is colonized somewhat later, with modern humans arriving roughly 45,000 years ago and encountering the Neanderthals who had lived there for hundreds of thousands of years. The two species coexist for perhaps 5,000 years, a period during which interbreeding occurs and during which Neanderthal populations steadily decline. By 40,000 years ago, the Neanderthals are gone. Europe belongs to sapiens. The colonizers bring with them art, music, sophisticated tools, and, likely, diseases against which the Neanderthals have no immunity. The pattern of arrival, coexistence, and replacement will repeat itself throughout human history. The Americas are the last major landmass to be reached. During the last glacial maximum, roughly 26,000 to 19,000 years ago, sea levels dropped by over 120 meters, exposing the Bering Land Bridge between Siberia and Alaska. Human populations in Northeast Asia cross into the Americas, likely in multiple waves, beginning perhaps 20,000 to 15,000 years ago. They spread south with astonishing speed, reaching the southern tip of South America by at least 14,500 years ago. In perhaps 5,000 years, humans colonized 2 entire continents. Nothing in the history of mammalian dispersal comes close. And wherever humans arrive, the large animals die. This is the Pleistocene megafaunal extinction, and the pattern is consistent across every continent. Australia loses its giant marsupials, the diprotodonts, giant wombats, marsupial lions, and enormous short-faced kangaroos within a few thousand years of human arrival. North America loses its mammoths, mastodons, giant ground sloths, dire wolves, saber-toothed cats, and American horses. South America loses its glyptodonts, toxodons, and native ungulates. In total, roughly 60% of all large mammal species worldwide go extinct between 50,000 and 10,000 years ago. The debate over whether climate change or human hunting caused these extinctions has raged for decades, but the evidence increasingly favors humans as the primary driver. The timing of extinctions correlates far more closely with human arrival than with climate events. Africa, where megafauna co-evolved with hominins over millions of years and had time to develop defensive behaviors, retains most of its large mammals. Australia and the Americas, where animals had no prior experience with human predators, suffer the worst losses. The megafauna had no fear of us. They had never needed to. By the time they learned, it was too late. The woolly mammoth, perhaps the most iconic of the Pleistocene megafauna, deserves particular mention. Once ranging across Europe, Asia, and North America in herds of millions, the mammoth is driven to extinction on the mainland by roughly 10,000 years ago. A tiny population survives on Wrangel Island in the Arctic Ocean until approximately 4,000 years ago, meaning that mammoths were still alive when the Egyptian pyramids were being built. They outlived their continental relatives by 6,000 years, only to die out on their island refuge, likely from inbreeding depression and loss of genetic diversity. A species that survived multiple ice ages could not survive us. By roughly 12,000 years ago, Homo sapiens has colonized every continent except Antarctica. From the Arctic tundra to the tropical rainforest, from the Himalayan highlands to the Pacific Islands, humans have adapted to every terrestrial environment on the planet. They have developed hundreds of distinct languages, dozens of tool traditions, and a bewildering variety of cultural practices. They have art, religion, music, and oral traditions stretching back thousands of years. They are, by any ecological measure, the most successful large mammal in the history of the planet. And they're about to become something else entirely. But let us pause before we rush into agriculture and civilization and all the rest. For 95% of Homo sapiens' existence, we lived as hunter-gatherers, small bands of 30 to 150 individuals, moving through landscapes they knew intimately, eating diets far more varied than our own, working perhaps 4 to 6 hours a day, and spending the rest telling stories, making music, playing with children, and watching the stars. Some anthropologists argue this was the original affluent society, a life richer in leisure, social connection, and environmental knowledge than anything that followed. We traded it for wheat, hierarchy, and tax collectors. Whether that was a good deal remains, to put it charitably, debatable. 12,000 years ago, at the end of the last ice age, the world is warming. Glaciers retreat, sea levels rise, forests spread into formerly frozen landscapes. And in several regions of the world, independently and almost simultaneously, human societies make a decision that will prove more consequential than any battle, any invention, any philosophical insight in the history of the species. They begin to farm. They plant seeds. They tend animals. They stop moving. And in that moment, for better and for worse, the trajectory of human civilization is set. The transition from foraging to farming does not happen overnight. In the Fertile Crescent, the arc of relatively well-watered land stretching from the Jordan Valley through southern Turkey to Mesopotamia, the process takes roughly 2,000 years. Wild wheat and barley are gradually domesticated through selective harvesting of the largest, most easily gathered seeds. Wild goats and sheep are corralled, fed, bred for docility and milk production. By about 10,000 years ago, the first Neolithic farming villages the landscape, Jericho, Catalhoyuk, Abu Huraira, permanent settlements built of mud, brick, and stone, housing hundreds of people. Agriculture is independently invented in at least half a dozen locations worldwide. In China, rice and millet are domesticated along the Yangtze and Yellow Rivers. In Mesoamerica, maize is painstakingly bred from the wild grass teosinte over thousands of years. In the Andes, potatoes and quinoa. In the Sahel, sorghum and millet. In New Guinea, taro and yams. Each center develops its own suite of crops and animals, its own techniques, its own cultural adaptations. The agricultural revolution is not a single event. It is a global convergence, a species simultaneously arriving at the same idea from different starting points. The consequences of farming are immense and not uniformly positive. On the one hand, agriculture produces surplus, more food than a single family can consume. Surplus enables specialization. If not everyone needs to grow food, some people can make pots, weave cloth, build walls, or conduct rituals. Specialization enables complexity. Priests, soldiers, artisans, administrators. Complexity enables hierarchy. Chiefs, kings, taxes, laws. Within a few thousand years of adopting agriculture, small egalitarian bands of foragers are transformed into stratified societies with sharp divisions between the powerful and the powerless. On the other hand, agriculture brings misery in quantities the foraging world never knew. Farmers work harder than hunter-gatherers for a less diverse diet in larger, more crowded, less sanitary settlements. Infectious diseases bred in the close quarters of human and animal cohabitation become epidemic. Smallpox, measles, influenza, tuberculosis, all zoonotic diseases that jump from domesticated animals to their human keepers. Malnutrition increases as diverse foraging diets are replaced by monotonous grain-based meals. Skeletal evidence shows early farmers were shorter, sicker, and more poorly nourished than their foraging ancestors. We chose quantity over quality. The species has been arguing about this trade-off ever since. By roughly 3,500 BCE, the first true civilizations emerge in the river valleys of the ancient world. Sumer, in southern Mesopotamia, between the Tigris and Euphrates rivers, is traditionally considered the world's first civilization. A network of city-states, Ur, Uruk, Eridu, Lagash, each one containing tens of thousands of inhabitants, governed by kings and priests, sustained by irrigated agriculture, and defended by organized armies. Uruk, at its peak around 3000 BCE, may have been the largest city on Earth, with a population of 40,000 to 80,000 people. With civilization comes its greatest invention, writing. The Sumerians developed cuneiform, a system of wedge-shaped marks pressed into wet clay tablets with a reed stylus, around 3400 BCE. Initially used for accounting, recording grain stores and livestock, writing quickly expands to encompass law, literature, religion, and science. The earliest known literary work, the Epic of Gilgamesh, is Sumerian. It tells the story of a king who seeks immortality after the death of his friend Enkidu and fails. The very first story ever written down is about the inevitability of death. Humanity starts its literary career with its most fundamental anxiety. Egypt develops along the Nile, unified under a single pharaoh around 3100 BC. The Indus Valley Civilization, with its remarkably planned cities of Mohenjo-Daro and Harappa, flourishes from roughly 2600 to 1900 BCE. The Shang dynasty in China emerges around 1600 BCE, bringing bronze metallurgy, divination, and the earliest Chinese writing. Each civilization develops independently, each with its own writing system, its own cosmology, its own social structure. But they share common features: centralized authority, monumental architecture, organized religion, social stratification, and warfare. The template of civilization, once invented, proves remarkably consistent. Mathematics emerges as a practical necessity. You cannot build a pyramid, administer an empire, or predict the flooding of the Nile without numbers. The Babylonians develop a base 60 number system whose legacy survives in our 60-minute hour and 360-degree circle. The Egyptians invent practical geometry to resurvey flooded farmland. The Indians will later contribute the concept of zero and the decimal place value system that we still use today. Mathematics begins as accounting and land measurement. It will eventually become the language in which the universe itself is written. The first millennium BCE witnesses what Karl Jaspers called the Axial Age, a period of extraordinary philosophical and religious innovation across the civilized world. In Greece, Socrates, Plato, and Aristotle lay the foundations of Western philosophy. In India, the Buddha and Mahavira propose radical paths to liberation from suffering. In China, Confucius and Laozi articulate competing visions of social order and cosmic harmony. In Persia, Zoroaster preaches a cosmic struggle between good and evil. In Israel, the prophets articulate ethical monotheism. Across the ancient world, independently, humans begin to ask the same questions. What is justice? What is the good life? What happens when we die? Empires rise and fall with a regularity that begins to feel almost biological. The Akkadian Empire, the first empire in history, unifies Mesopotamia under Sargon around 2334 BCE and collapses within 2 centuries. The Egyptian New Kingdom reaches its zenith under Ramesses II and declines into foreign domination. The Assyrian Empire, notorious for its cruelty, dominates the Near East for centuries before being annihilated in 612 BCE. The Persian Achaemenid Empire, the largest the world has yet seen, stretches from Egypt to India before Alexander of Macedon destroys it in a decade of brilliant, reckless conquest. Rome begins as a cluster of mud huts on the Tiber River and becomes, over 1,000 years, the most powerful political entity the Western world has ever known. At its height under Trajan in 117 CE, the Roman Empire encompasses the entire Mediterranean basin, 70 million people, governed by a single legal system, connected by 80,000 kilometers of roads, and defended by a professional army of 400,000 soldiers. Rome's contributions: law, engineering, administrative systems, the Latin language that spawns French, Spanish, Italian, Portuguese, and Romanian, will shape Western civilization for the next 2 millennia and beyond. But empires are not the whole story. In China, the Qin and Han dynasties unify the Eastern world under centralized bureaucracies of staggering sophistication. The Maurya and Gupta empires foster a golden age of Indian science, mathematics, and art. The trading networks of the Silk Road connect Rome to China, transmitting goods, ideas, diseases, and technologies across 8,000 kilometers of steppe, desert, and mountain. The Indian Ocean trade routes link East Africa to Southeast Asia. By the first centuries of the Common Era, the Old World is for the first time a single connected system. What happens in Rome affects Chang'an. What happens in India ripples to Alexandria. Along these trade routes travel not only silk, spices, and gold, but also ideas and, more devastatingly, pathogens. The Antonine Plague, a 165 to 180 CE, probably smallpox, kills an estimated 5 to 10 million people across the Roman Empire. The Plague of Justinian in 541 CE, caused by Yersinia pestis, the same bacterium that will cause the Black Death 800 years later, kills perhaps 25 to 50 million across the Mediterranean world. Connectivity is a double-edged sword. The same networks that transmit philosophy and commerce also transmit death. Globalization is not a modern invention. Neither are its consequences. By roughly 500 CE, the ancient world order has collapsed and reconstituted multiple times. Rome has fallen in the west and transformed into the Byzantine Empire in the east. The Han dynasty has fractured into warring kingdoms. The Gupta Empire has declined. Islam is about to emerge in Arabia and, within a century of Muhammad's death in 632, create an empire stretching from Spain to Central Asia. The medieval world inherits the knowledge, the trade routes, and the diseases of the ancient world, and begins the slow, uneven process of recombining them into something new. The stage is being set for an acceleration that will make all previous history look like prelude. In the year 1543, 2 books are published that will detonate the medieval worldview. Nicholas Copernicus publishes De Revolutionibus Orbium Coelestium, arguing that the Earth orbits the Sun, not the other way around. And Andreas Vesalius publishes De Humani Corporis Fabrica, the first accurate atlas of human anatomy, based on actual dissection rather than ancient authority. In the same year, by sheer historical coincidence, 2 men simultaneously insist that truth must come from observation, not tradition. It is the opening salvo of the scientific revolution, and it will change absolutely everything. The scientific revolution, spanning roughly the 16th through 18th centuries, is not a single discovery or a single method. It is a shift in attitude, the radical, dangerous, historically unprecedented idea that the universe operates according to discoverable natural laws, and that human reason, aided by systematic observation and experiment, can uncover those laws. Galileo points his telescope at Jupiter and sees moons. Newton formulates the law of universal gravitation. Harvey maps the circulation of blood. Each discovery is a brick pulled from the edifice of received wisdom. The edifice does not fall. It simply becomes irrelevant. Isaac Newton, born in 1642, the year Galileo died, is arguably the most consequential scientist in history. His Principia Mathematica, published in 1687, demonstrates that the same force that pulls an apple to the ground also keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. Gravity is universal. The heavens and the Earth obey the same laws. This is a shattering insight, demolishing 2,000 years of Aristotelian distinction between celestial perfection and terrestrial corruption. The cosmos, it turns out, does not care about our categories. The Enlightenment of the 18th century extends the logic of the scientific revolution into politics, economics, and morality. If the universe operates by rational laws, perhaps human society can too. Locke argues for natural rights, Voltaire for freedom of expression, Montesquieu for the separation of powers, Rousseau for the social contract. The American and French revolutions put these ideas to the test with mixed results. Liberty, equality, fraternity, noble ideals, imperfectly realized, violently contested, and still works in progress 250 years later. But the transformation that truly reshapes the planet begins not in a library, but in a workshop. In 1769, James Watt patents an improved steam engine, and with it, the Industrial Revolution begins. For the first time in human history, a society powers itself not with muscle, wind, or water, but with fossil fuels, coal, and later oil and natural gas. These fuels are stored sunlight, the compressed remains of Carboniferous forests and Mesozoic plankton, 300 million years of solar energy, locked in carbon, now released in centuries. It is the ultimate withdrawal from the planet's savings account. The scale of the transformation is difficult to overstate. In 1800, the global population is roughly 1 billion, virtually all of them powered by human and animal muscle. By 1900, it has reached 1.6 billion, and factories in Britain, Germany, and the United States are producing steel, chemicals, and manufactured goods at rates unimaginable a century earlier. Railways span continents. Telegraph wires carry messages at the speed of light. Electric lighting turns night into day. The world of 1900 is more different from 1800 than 1800 was from the Roman Empire. The 19th century also produces the two scientific insights that will define modernity. In 1859, Charles Darwin publishes On the Origin of Species, demonstrating that all living things are related through descent with modification, driven by natural selection. Life is not designed, it is evolved. In 1865, James Clerk Maxwell unifies electricity and magnetism into a single theory, predicting the existence of electromagnetic waves. Darwin rewrites biology. Maxwell rewrites physics. Together, they replace a universe of divine purpose with a universe of natural law. Many people find this liberating. Many find it terrifying. Both reactions are appropriate. The 20th century arrives with the force of a detonation. In 1905, a 26-year-old patent clerk in Bern publishes 4 papers that reshape physics forever. Albert Einstein demonstrates the reality of atoms, explains the photoelectric effect, introduces special relativity, and derives E equals mc squared. In 1915, he follows with general relativity, revealing that gravity is not a force but the curvature of space-time caused by mass and energy. The universe is not what Newton thought it was. It is stranger, more flexible, and more beautiful. Quantum mechanics, developed in the 1920s by Heisenberg, Schrödinger, Dirac, Born, and others, reveals that at the atomic scale, reality is fundamentally probabilistic. Particles do not have definite positions until measured. They exist in superpositions of states. They are entangled across distances in ways that Einstein called spooky action at a distance. Quantum mechanics is the most precisely tested theory in the history of science, accurate to 14 decimal places. It is also, by common consensus, deeply weird. As Richard Feynman put it, if you think you understand quantum mechanics, you do not understand quantum mechanics. The 20th century also reveals the darkest capacities of the human species at industrial scale. 2 world wars kill an estimated 80 to 100 million people. The Holocaust murders 6 million Jews and millions of others in an act of bureaucratically organized genocide. The development and use of nuclear weapons at Hiroshima and Nagasaki in August 1945 demonstrates that humanity now possesses the ability to destroy itself. The same species that composed the Brandenburg Concertos builds Auschwitz. The same species that discovered penicillin invents nerve gas. The contradictions are not resolvable. They are us. The second half of the 20th century brings an acceleration that makes the first half look sluggish. The discovery of DNA structure in 1953. The space race and the moon landing in 1969. The development of the microprocessor in 1971, the personal computer in the 1980s, the World Wide Web in 1991, the sequencing of the human genome in 2003, the smartphone in 2007. Each innovation arrives faster than the last, the interval between transformative technologies compressing from centuries to decades to years. The curve is exponential. Where it leads is anyone's guess. The global population, which took 200,000 years to reach 1 billion in 1800, reaches 2 billion in 1927, 3 billion in 1960, 4 billion in 1974, 5 billion in 1987, 6 billion in 1999, 7 billion in 2011, and 8 billion in 2022. Each additional billion arrives faster than the last. The growth is driven by advances in agriculture, medicine, and sanitation, which have increased life expectancy, reduced child mortality, and enabled the feeding of billions through industrial farming, synthetic fertilizers, and the Green Revolution. We have, by sheer ingenuity, outrun Malthus. For now. But the cost of this expansion is being levied on the planet itself. Since the Industrial Revolution, atmospheric CO2 concentrations have risen from roughly 280 parts per million to over 420 parts per million, a level not seen in at least 800,000 years and possibly not in 3 million years. Global average temperatures have risen by approximately 1.2 degrees Celsius above pre-industrial levels. Ice sheets in Greenland and Antarctica are losing mass at accelerating rates. Sea levels are rising. The chemistry of the oceans is shifting. We are running a geological experiment on our own planet, with no control group and no option to stop the trial. The term Anthropocene has been proposed for our current geological epoch, the age in which human activity is the dominant influence on Earth's climate and environment. Whether or not it is formally adopted by geologists, the concept is undeniable. Humans have altered more than 75% of the Earth's ice-free land surface. We have redirected the flow of rivers, flattened mountains for mining, and created artificial islands. We produce more than 380 million tons of plastic per year. We have moved more earth and rock than all the world's rivers combined. We are a geological force, whether we intend it to be or not. The current rate of species extinction is estimated at 100 to 1,000 times the background rate, leading many biologists to classify the present as the sixth mass extinction in Earth's history. The last mass extinction killed the dinosaurs. This one is being caused by a single species of ape. Habitat destruction, pollution, climate change, overexploitation, and invasive species are driving populations of vertebrates, insects, and plants into steep decline. The Living Planet Index shows an average 69% decline in monitored wildlife populations between 1970 and 2018. This is not a forecast. This is a measurement. And yet, in the same species that produces this destruction, something extraordinary persists. The Voyager 1 spacecraft, launched in 1977, now travels through interstellar space, carrying a golden record of human sounds, images, and greetings in 55 languages. The James Webb Space Telescope peers back to the first galaxies. The Large Hadron Collider recreates conditions a trillionth of a second after the Big Bang. Artificial intelligence systems compose music, write poetry, and fold proteins. The same brain that evolved to track antelope on the savannah now decodes the structure of space-time. We are magnificent and terrible in equal measure. Artificial intelligence, in particular, represents a threshold whose full implications remain unclear. Large language models, neural networks, and machine learning systems are advancing at a pace that surprises even their creators. The question of whether artificial general intelligence, a system that matches or exceeds human cognitive ability across all domains, will emerge in years, decades, or centuries is the subject of intense debate. If it does, it will be the most consequential event since the cognitive revolution. A new kind of mind, born not from carbon and evolution, but from silicon and engineering. The cosmos contemplating itself through an entirely new medium. We stand at an extraordinary moment. For the first time in 4.5 billion years, a species on this planet possesses the ability to deliberately alter its own genome, colonize other worlds, and build minds from scratch. It also possesses the ability to render its own planet uninhabitable, exterminate its own civilization with nuclear weapons, and drive the biosphere into a mass extinction rivaling the Permian. Both outcomes are plausible. Both are being actively pursued by different factions of the same species. The next century will determine which path prevails. The stakes are not human. They are cosmic. Everything ends. This is not a moral lesson. It is not a metaphor. It is thermodynamics. The second law, the most melancholy of all physical laws, states that the entropy of a closed system tends to increase over time. Order decays into disorder. Heat flows from hot to cold. Energy disperses. The universe, taken as a whole, is a closed system, and it is running down. Every star that burns, every thought you think, Every breath you take increases the total entropy of the cosmos by some tiny, irreversible amount. We are all, every one of us, contributing to the end of the universe. You're welcome. Let us begin with the death we know best. In approximately 5 billion years, the sun will exhaust the hydrogen fuel in its core. Hydrogen shell burning will cause the outer layers to expand, transforming the sun into a red giant roughly 250 times its current diameter. Its surface will cool to a dull red, but its total luminosity will increase 1,000-fold. Mercury will be consumed. Venus will be consumed. Earth's fate is uncertain. It may be swallowed, or it may survive in a scorched, sterilized orbit just beyond the swollen sun's surface. Either way, Earth as a living world ends long before the sun itself dies. In fact, Earth's habitability will end much sooner than that. As the sun slowly brightens over geological time, roughly 1% every 100 million years, it will eventually push Earth's surface temperature past the threshold for liquid water. Current models suggest this will happen in roughly 1 to 1.5 billion years. The oceans will evaporate. Water vapor, a potent greenhouse gas, will trigger a runaway greenhouse effect, turning Earth into a Venus-like hell world. For 100 degrees Celsius, crushing atmosphere pressure, no surface water, no life. Our planet's habitable window is already more than 3/4 closed. After its red giant phase, the sun will shed its outer layers in a planetary nebula, a beautiful, glowing shell of ionized gas expanding into space. At the center, the exposed core will remain, a white dwarf, roughly the mass of the sun compressed into a sphere the size of the Earth. Initially very hot, it will cool over billions of years, dimming from white to yellow to red to brown, and eventually, over timescales far exceeding the current age of the universe, to black. A black dwarf, a cold, dark, crystallized ember. The sun's last act is a slow, dignified fade to nothing. Before the sun dies, something dramatic will occur on a galactic scale. In approximately 4.5 billion years, the Milky Way and the Andromeda Galaxy will collide. The two galaxies are currently separated by 2.5 million light-years and approaching each other at 110 kilometers per second. Their merger will take roughly 2 billion years, during which billions of stars will be flung into new orbits. Spiral arms will be destroyed, and the combined structure will eventually settle into a single, massive elliptical galaxy. Astronomers have named it Milkomeda, or sometimes Milkdromeda. Neither name will survive long enough to be used. Despite the violence of the merger, individual stellar collisions will be extraordinarily rare. Galaxies are mostly empty space. The average distance between stars in the Milky Way is about 4 light-years, and during the merger, that spacing will remain vast. Stars will be gravitationally redirected, not physically impacted. If any civilization survives on a planet during the merger, they will see a spectacular light show in their sky as Andromeda grows from a smudge to a continent of stars, but they will almost certainly not be hit by anything. Galactic mergers are violent to structures, but gentle to individuals. After the merger, star formation in the newly combined galaxy will continue for a time, fueled by the gas reserves of both galaxies. But the fuel is not infinite. Over tens of billions of years, the available gas will be consumed, locked into stars, white dwarfs, neutron stars, and black holes. New star formation will slow to a trickle and eventually cease entirely. The last stars to form will be red dwarfs, those miserly, long-lived, dim little furnaces that can burn hydrogen for trillions of years. The age of stellar creation, which began at cosmic dawn, will quietly come to an end. The stelliferous era, the age of stars, spans from roughly 150 million years after the Big Bang to perhaps 100 trillion years in the future. 100 trillion years sounds like an eternity, but it is a rounding error compared to what comes next. When the last red dwarf finally exhausts its hydrogen fuel and cools to a brown, then black dwarf, the universe enters what Fred Adams and Greg Laughlin have called the degenerate era. A universe of stellar corpses, white dwarfs, neutron stars, and black holes drifting through an ever-expanding, ever-cooling void. In the degenerate era, which stretches from 10 to the 14th years to roughly 10 to the 40th years after the Big Bang, the universe is dark. No stars shine. The only light comes from the occasional collision of brown dwarfs, the rare accretion event onto a neutron star or black hole, and the faint thermal glow of cooling white dwarfs. Galaxies, or what remains of them, are invisible archipelagos of dead stars and black holes, slowly evaporating as gravitational encounters fling individual objects into intergalactic space. The cosmos is dying, not with drama, but with relentless, patient erosion. On timescales of 10 to the 19th to 10 to the 20th years, galaxies themselves dissolve. Gravitational interactions between stellar remnants gradually eject most objects into intergalactic space. The galaxy, once a gravitationally bound system of hundreds of billions of stars, loses its members one by one, like a crowd dispersing after a concert. What remains at the center is the supermassive black hole, now surrounded by a thin retinue of orbiting remnants. Eventually, even these are consumed or ejected. The black hole sits alone in an emptying universe. But even black holes do not last forever. Stephen Hawking's 1974 calculation shows that black holes emit thermal radiation due to quantum effects at the event horizon. This Hawking radiation is vanishingly faint for astrophysical black holes. A solar mass black hole has a temperature of about 60 nanokelvins, far colder than the current cosmic microwave background. It actually absorbs more radiation than it emits. But as the universe expands and the CMB cools toward absolute zero, eventually the black hole's temperature will exceed that of its surroundings. At that point, it begins to evaporate. The evaporation timescale depends on mass. A stellar mass black hole, about 10 solar masses, will take roughly 10 to the 67th years to evaporate. A supermassive black hole of 1 billion solar masses will take roughly 10 to the 97th years. The most massive black holes conceivable might last 10 to the 100th years, a googol years, a number so large it makes the current age of the universe, a mere 1.38 times 10 to the 10th years, look like a rounding error's rounding error. But even this is finite. Given enough time, every black hole in the universe will evaporate. As a black hole evaporates, it gets hotter and smaller. The process accelerates exponentially in the final moments. The last fraction of a second is explosive. The remaining mass is converted into a burst of high-energy particles and radiation, a final, furious scream of energy before the black hole winks out of existence. The last black hole in the universe will die this way, perhaps 10 to the 100th years from now, in a flash so brief and so far in the future that no structure, no intelligence, no memory will exist to witness it. The last event in the history of gravity. There is one more possibility to consider, and it is among the strangest in all of physics. Proton decay. The Standard Model does not predict it, but many grand unified theories do. If protons are not perfectly stable, if they decay with a half-life of perhaps 10 to the 40th years, then all ordinary matter will eventually disintegrate. Every atom, every molecule, every crystal in the universe will dissolve into leptons and photons. If proton decay is real, then in the far future, there will be no atoms. No chemistry, no solid matter of any kind, just particles and radiation drifting apart forever. After the last black hole evaporates, the universe enters what Adams and Laughlin call the dark era. It is in every meaningful sense the end. The cosmos is a vast, cold, nearly empty expanse of photons, neutrinos, electrons, and positrons, all separated by distances so immense that they will never interact again. The temperature of the universe approaches but never quite reaches absolute zero. Entropy is at its maximum. No thermodynamic work can be done. No energy gradients exist to drive any process. Nothing happens. Nothing can happen. Nothing will ever happen again. The heat death of a universe is not an event. It is an eternity. There is no moment at which you can say, here, the universe has died. Instead, it asymptotically approaches a state of perfect equilibrium, a state in which the temperature is the same everywhere, the density is the same everywhere, and every possible thermodynamic process has been completed. It is the ultimate expression of the second law. Maximum entropy, minimum information, a cosmos that has forgotten everything it ever was. There are alternatives. Some physicists speculate that a quantum fluctuation in the vacuum, the same kind of fluctuation that may have sparked our universe in the first place, could occur again, given enough time. The Boltzmann brain hypothesis suggests that, over sufficiently vast timescales, random fluctuations could spontaneously assemble conscious observers out of the vacuum. Others propose that the universe might undergo a vacuum decay event, a sudden phase transition in which the quantum vacuum drops to a lower energy state, destroying everything in an expanding bubble traveling at the speed of light. You would not see it coming. You would simply cease to exist. But these are speculations, and our documentary must return, in its final moments, to what we know. We know that the cosmos began 13.8 billion years ago in an event of unimaginable violence. We know that from that violence emerged hydrogen and helium, and from those elements, stars, and from those stars, heavier elements, and from those elements, planets, and from at least one planet, life. We know that life evolved, diversified, suffered, endured, and eventually produced a species capable of reconstructing the entire story. That is an extraordinary chain of events. That is worth remembering. We are made of atoms forged in the cores of stars that died before the sun was born. We carry in our cells the genetic code that links us to every living thing that has ever existed on this planet. We inhabit a cosmos that, for a brief, improbable interval between the fire of its beginning and the silence of its end, has produced complexity, beauty, suffering, and consciousness. This interval will not last. The stars will go out. The atoms will decay. The void will reclaim everything. But not yet. Right now, in this moment, on this small blue world orbiting an unremarkable star in an unremarkable galaxy, the universe is aware of itself. Through your eyes, the cosmos looks out and comprehends its own history. That is not nothing. In a universe that will spend the overwhelming majority of its existence in a state of cold, empty, unconscious silence, the fact that there was once a brief moment when matter organized itself into beings that could ask why may be the most remarkable thing that ever happens. We are the universe's way of knowing itself, and that, in the face of eternity, is enough.